do I detach the chat? Pop out chat. Sweet. Okay. Well, where's my analysis homework? Nope. There it is. Oops. Lost my live preview. Okay. I'm going to just work on writing that out. Where do you think you will be in 6 or 7 years? Can't help but wonder if there's some significance to the choice of those numbers. I'm just going to write this out so that I don't have to worry about it later. Sequence a sub n equals x to the n converges to 0. Prove that the sequence a sub n equals x to the n converges to 0 is absolute value x less than 1 and diverges. Oh, this should be an if, not an is, I don't think. My teacher is quite dumb. What's up, Owen? How come Baltin Bujadozo like originally had the #1 poster title but then lost it and Owen took it, but he's like the 4th message. Don't get that. What homework are you doing? Yes, math is my major. Yeah. Linear algebra. Is it like proof-based linear algebra? Or is it like plug and chug based? Do this vector multiplication. Okay. Converges to 0 if... Is there like an abs? Yeah. Abs x less than 0 and diverges if abs x greater than 1. Man, I actually hate real analysis, but new batch of the big Steen files dropped. Did you see? No, what were the highlights? I'm pretty convinced at this point, to be honest, just based on like how outrageous the media is getting, like that it's like it's not. I guess there's definitely maybe some truth to it, but it's like, does it? It's just like so. It's like too entertaining. It's like there's just too. This is a little bit worryingly attention capturing. And if you think about it, like even like news sources that people consider really reliable, they have like fact checkers, they have all the staff, they have every one of the production teams that makes things happen, and like they're definitely incentivized towards making content that's like reaction worthy, so people will keep watching it. And I don't know, that's a little like weird to me. Like if you think about news outlets, for some reason people tend to separate them from like companies, but they're just like capitalistic enterprises like any other company. They want to be profitable so they can keep existing, and like that profit model I think can kind of warp their behavior a little bit. Yeah, big Ted Kaczynski fan. Oh, I had this thought about that I could do with Typst. So what's really annoying, I kind of partially did this problem on last stream, but so if I type proof, right, I want that to just always show up as like italic colon, and I was thinking, I think there's a way to do that in Typst. You could do like show regex, and then I pass in proof. I guess I'll do capital. Could I do like it text style, or you can do underscores, I think. Oh, that's awesome. That is sick, dude. So now, like, whenever I type proof, I don't have to type the rest of the, like, I don't have to italicize it. Just boom, proof. Okay, well, I have to make it capitalized. Or maybe I'll just do lowercase, but I think that's pretty cool. And actually, even like, yeah, that's nice. Typst is really cool. All right, let me get back to typing this up. Okay, problem 2. And maybe I'll think about each of the problems a little bit. Is my IP showing on the right? Does that like matter though? Bro, what do you use in nvim for deleting a word in insert mode? Something like control backspace? Because Vim doesn't support control backspace. Yeah, I use control W. I wish I could use control W on other things. Yeah, it's literally a local host. Like, what are you gonna do? Wish there was a good Typst integration org mode. I mean, you could write one. All right. If a of n plus 2 equals a of n plus 1 plus a of n, divide by 2, for all n greater than or equal to 1. I think my template is missing. I can grab it from here. Yep. Okay. Show that a sub n. You can just get that arrow by typing that, I think. A sub 1 a sub 1 boom plus 2 a sub 2 for 3. Man, I swear the problem with engineering degrees or like math is you like sacrifice your social life in order to have a better job in the future. Just because like some of this stuff just takes so goddamn long to like sink in. Seven x plus 1. A real sequence x sub n satisfies 7 times x n plus 1 equals x to the 3 sub n plus 6 for n greater than or equal to 1 if x sub 1 equals 1/2. There was a program that allowed you to like OCR LaTeX off your homework, but that doesn't really exist for Typst yet. Oh. Not that I know of. Like math picks. Oh wait, is this it? It's in JavaScript. Install. Run. Ensure you're in the repo. How does this actually work? Has 105 stars. Has anyone actually used this? Dots OCR? Oh wow. And they support Typst? Hello. Does Typst let you export an SVG? It sure does. If it does, then I could try developing a package for org mode. It wouldn't be so bad. Yeah, it absolutely exports SVGs. The theme is vague. Yeah. I don't know. I think I'm just going to type this out for now. Okay, that looks good. Prove that the sequences increases and find its limit, and then problem 4 and 5. Dude, real analysis is actually so hard. This is ridiculous. It's like kicking my ass. Plus I'm like hitting the ego realizations that like I'm not that cracked at anything. In exercise 3, what happens? Okay. I'm saying problem 3 because exercise always confuses me to type. It's got all those X's and C's. I never know which order. X sub 1 equals 3/2. Or if X sub 1 equals 5/2. Hopefully I'm going to learn a lot today. I kind of want to stream more just because it's really good for discipline, you know? When I'm on my own, sometimes I'm just like slacking AF. But if people are watching you, then like you can't really slack without it being pretty embarrassing. All right, and then final one. Sheafification. What? Oh, sheafification of G. This is a YouTube channel I was supposed to look at. I'll just throw that into my browser for later. Oops. Okay. I'll drop a follow on GitHub. That'll remember. Follow. Cool. All right, problem 5. What is problem 5? Okay. If abs an less than 2. And abs an plus 2. God, this is annoying. Minus a n plus 1 less than or equal to 1/8 abs. Wow, this is a gnarly problem. Has anyone taken real analysis here? I've been talking to hella Europeans lately. I enjoy you guys. I was talking to this guy from Lithuania this morning, all about his experience with meditation. Surprising amount of Europeans in my audience. I just like hearing other people's accents too for a change. Solution. Write your solution here. Huh. What is that? Kind of easy? Is that first year math or something? Yeah, we got lots of Euro bros. Why are there so many Euro? I don't know. Back in the day, I used to spam hashtags for different European countries to try to diversify my audience. Lots of UK people. Alrighty. Absolutely brutal real analysis. I much prefer number theory. Real analysis is like... Actually, I want some advice on this if anyone's taken real analysis. My view is that so number theory is like the proofs are kind of longer and they feel more creative, whereas the proofs in real analysis are just like much more trivia based. It's like you have to just know that this theorem holds, and like the proofs are all kind of short, at least that I've had so far. They're only like five lines or something, or sometimes they're only like 2 lines, but you just have to know a lot. So I was thinking of like making like a database of all the important things I have to know, like all the theorems and stuff. Bro, you study computer major? No, not really. In Europe, real analysis is the first course you get in math physics major. Yeah, the European school system's just cracked, I guess. What's that country? What's that flag? I don't recognize it. Oh wow, that dropped a whole ass PNG. You just need a list of all the popular theorems and stuff, IMO, and lots of examples using the theorems. Oh, Nepal. Yeah, maybe I'll start writing them down as I go. Okay. So I hope there's someone here who knows real analysis, else I am fucked. but I did this last stream. Prove the sequence a sub n, and I want to formalize this work because I think it's somewhat butts. Looks like this stuff we learned in Calc 1. All right, great. You'll be able to help then. Prove the sequence x to the n converges to 0 if the absolute value of x is less than 0. It diverges if I think she meant, I might have mistyped that. Yeah, if x is less than 1. Okay. So in the case that I actually kind of want to start keeping like a notes document, common sense, and this is just going to be like things that I should why don't I use Zathra? I do use Zathra. I'm the maintainer of the Zathra tap. Okay, so I'm just gonna write down like every analysis definition I come across, and then we'll see which ones are frequent. But convergence is pretty important. My Zathra actually broke though, so let's see. Real analysis. I don't know if it's analysis déjà vu or analysis mathematical analysis. I think it's the déjà vu. Okay. See, I do use Zathra, shut up. Convergence. Definition. Okay, where is the definition of convergence? Are those the only two places in the whole book? Monotonic sequence of real numbers converges if and only if it's bounded. You see what I mean about these proofs being like two lines? Say the sequence is increasing, and we write, I've never seen someone write it like that, but okay. If a is less than a to the n plus 1 for all, and 1, 2, blah, 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 blah. If we say its sequence is decreasing, sequence is called monotonic if it's neither. Convergence or divergence of a monotonic sequence is particularly easy to determine, if and only if it's bounded. Where is the definition of convergence, though? What the fuck? What is this book? Yeah, that's wild. Raj Jr., thank you, I appreciate it. Mine keeps breaking every time I update. Yeah, that's about what the tap is. There's this guy who helps me maintain it. I actually let him do like all the work just because I'm really lazy. But yeah, Zathra's always breaking. All the time. Okay, convergence. All right, convergence. Where's the definition of convergence? There we go. All right. In a metric space is said to converge if there's a point in S with the following property. For every epsilon greater than 0, there's an integer. So we don't really need that junk above. Okay. N such that the distance of x sub n and some point is less than epsilon whenever n greater than big N. All right. We also say that x sub n converges to p, and we write x sub n converges to p, or n as n goes to infinity, or simply x of n converges to p. Definition of convergence implies that x of n goes to p if and only if the distance of x of n and p goes to 0. The convergence of sequence takes place in the Euclidean metric space R1. Fire. Okay, I'll send that away for now. So basically our distance is, I don't know, but there's a couple different definitions of that. What's a glowy? Oh. This is Firefox. Ooh, I found a couple of chickpeas on my desk. Classic event that goes down in this household. The chickpea find. Alrighty. So, last time, I'm going to go over this real quick, and then I'm going to call that guy. Do you have a different book? I also don't see how to do this first one. Johnny. I don't know how to say that, but yeah, I might have to call you or this other guy for, I don't know, for variety, but yeah, so this first one, like, didn't we solve this last time? I found more chickpeas. Man, I love chickpeas. Oh, it's the ambitious guy. All right, I'm gonna go through this, make sure I understand it. All right, so we want to show that this distance is less than epsilon. That's because that is the same thing as distance. You're just absolute value and subtracting them, I believe. That's the distance in, like, we could say the number line is like a metric space. And then we want to show that that's less than some epsilon for all n greater than n. And I'm not sure what I was going for with the if and only if spam here. It's kind of weird, but we know that, well, assuming this converges to 0, we've got, just eliminate the a, and that's less than epsilon, then we can take out the exponent, and then we can take the natural log or log base x using log properties, and then get n greater than log base x. And so that would be epsilon minus this a, absolute value epsilon minus a, those will cancel, is less than epsilon for all n. Okay. And then the other case, choose n to be, oh, that's, notation is messed up. Yeah, I'm just like formalizing this last time because I kind of forgot how we went about it. This should be like that. Yeah, I feel kind of shaky about this, to be honest. Prove the sequence. I just need a lot more practice with showing that a sequence converges. Is there like an algorithm you usually go about? You should define n in the proof. Yeah, this proof is like mostly scratch work. I want to formalize it. So yeah, this technically is a different book, I think. Examples. Define n in the proof. I appreciate the people glazing me in chat, but you'll get here one day and you'll be like, wow, that guy really did not know what he was talking about. All right, we got man, I love that there's just like people out there that know how to do this math that are like willing to hang around and help. That's fucking awesome. In the absolute value x less than 1 case, please note that ln absolute value x is less than 0, so dividing by it flips the inequality. Equivalently, set b equal to 1 over absolute value x is greater than 1, and choose n greater than log b 1 over epsilon. So absolute value x to the n less than epsilon for all n. I think the general idea of lim x to the n to infinity is the same as lim e to the n ln x to infinity, and it's much easier to throw the lim for n ln x to infinity than x to the n. All right, well, it's probably fine if I... Oh, I'm watching your stream right now. I got someone who might be willing to hop on a call and explain this nonsense to me. Is there an algorithmic way to approach Hold on.
Hello.
Gotta fix my mic. Hello? Can you hear me?
Yep, I can hear you now. How are you?
Yo, how's it going? How are you?
I'm good, I'm just watching the stream in the background while I'm reading some stuff, so.
Oh, awesome. Yeah. And so you have some kind of math background, as I understand it.
Yeah, so I graduated in 21, to be fair. It's been a minute, but I work in a research role with mathematics still. So, and university I graduated from was ranked 7 in the world, so, and also have a master's in maths, so it was pretty good.
Wow. Yeah.
You know.
Yeah.
I wouldn't say the best, but it's decent. Hopefully my math skills are anyways.
Yeah.
But yeah.
And so you use like actual pure math on a day-to-day basis for work?
Yeah, so I work in a fund. So a lot of the stuff I do is with a subject called stochastic calculus. You can have a quick look on the wiki, see what it looks like. But yeah, that's a lot of pure maths. Most of my job is trying to solve like these partial differential equations which have like randomness attached to it. So that's kind of a lot of what I'm doing at the moment in like I think some people in chat, if they know, then they know. It's kind of one of those situations. Same way, I don't know a lot of the stuff you do, you do so much. This computer science stuff is stuff that's well beyond, even my ability. So I literally, my computer science goes as far as being able to kind of write some Python code, play around on Excel, a little bit of, VBA, which you might not know about. It's so old, and it's like these old, people that are telling me to keep using it as legacy code. But yeah, it's a bit fun though watching someone new kind of, struggle around a little bit. That's the whole point of maths, though, right? To struggle and to keep trying at it. So it's good seeing it.
Yeah. I think a lot of people like to see the struggle too, because it's, I don't know, it's not often shown just how difficult it can be to build intuition for some of this stuff.
Yeah, and also you're doing it in front of, a lot of people.
Yeah.
I was doing it in my room by myself, struggling away.
Yeah.
Yeah. It's different, but yeah. I mean, I'm looking through some of the problems you're looking at right now.
Mm-hmm.
So those are like, where you'd start off in real analysis. But the book you're using looks quite, in my opinion, difficult.
Yeah.
Definition that you have is quite a difficult definition, no?
You mean the definition for convergence I was looking at with distance?
Yeah. So I didn't look at metric spaces till my second year. So as a start off, I used a different definition.
Yeah.
Because metric spaces, it's just like another level of complexity you add to the problem, right? Where you don't really need to be concerned with it. But I don't know what your opinion is. We can work with this one as well if you want to. It's kind of it's your approach. It's kind of up to you as in how you want to. Whatever interests you, right? That's what's going to keep you motivated at the end of the day.
Yeah, I mean, I think using the definition in my class, that's a. I'm actually really confused because I have two different textbooks. Um,
Hmm.
Currently, I don't know how I got that second one, but my PDF reader is like really corrupt. Just a kind of a Linux
Do you remember
problem.
what the book names were? I know the
I can
second one
check.
looks
Yeah,
like. If you let me know, then I'll. I've seen quite a few, so maybe I know them. Hopefully,
um,
maybe. I
mathematical
know the
analysis
definition.
by Tom Apostle.
Yeah, so that's one. And then you said the other one?
The other one, let me open actually. This one is a weird. Oh, this is also Apostle.
So yeah, I've never. I've read one of Apostle's editions, and I didn't see that definition there. So, but these books are quite old as well.
Yes.
Let me know the. There's a famous book that's come out recently that people like quite a lot. Um, it's called Understanding. Let me just make sure I get the name right, and I'll send it to you on Discord.
Yeah.
I'm sure you can find it, falling off the internet somewhere. You don't have to go around and buy it, but send you the book. I'll just send you what's typed in Google and then see the first link. That
Okay.
book, I've kind of helped a few people. Usually I do like a lot of volunteering tutoring
Mm-hmm.
around where I grew up because it's a bit of an underprivileged area. So that's the book I give people, and they seem to really like it. So I thought I'd shoot it to you. It does two things, right? One, it gives you like a bit more of an introductory level, but two, it builds that intuition. So I think intuition is like a really strong tool you can have.
Yes.
Um, the other thing I was going to say for this problem when we start is actually to plot some example sequences, which you can do easily.
Hmm.
So if we go to this book and have a look, if you scroll down, it's been a couple months since I've looked in the book. If we go to the contents, um, we'll find, where is the definition?
Is there a
I'll shoot you the page number in a second. I've got it open as well. Yeah, it should be around page 42. Yeah, page 43, or if you, yeah, page 43, definition 223.
convergence
Don't
of
worry
the
about the
sequence?
first chapter. The first chapter is kind of trying to explain to you what the real numbers are, but you can
Right.
use your intuition to get through most of it.
Yeah.
So if you have a look at that definition, see what you think about that. Makes it easier to wrap your head around.
For every possible number epsilon, there exists an n in the natural numbers, such that whenever n is greater than or equal to n, or whenever little n, then it follows that absolute value a of n minus a is less than epsilon. Yeah, this is much more familiar than that. They are
Exactly.
essentially saying the same thing, though.
Yeah,
Correct.
it's the exact same thing. It just, when you introduce that level of abstraction, it just makes it harder on yourself, right? You don't need it really. It's
Right.
for your problem. You just want to keep your tools as kind of sharp as possible, right?
Yes, I see. Yeah. Um,
So in terms of the problem then, so if we have a look at the problem, let's try and do some, match the shape to the whole, kind of
right.
see what you can match. And then an easy kind of starting would be to plot some examples. Have you ever heard of Desmos, by the way?
Yeah, sure.
Yeah, you can just chuck some examples on there as well.
Yeah. Really, for
Yeah, see if what they're saying is true. Like, is the problem actually true? Is it false? Obviously, it's probably true, and it is true. But it gives you intuition, right? Like, you can learn all about object-oriented programming, but if you don't actually start building like actual systems or actually deploying it in any way, you never really get an understanding.
right.
Uh, yeah, that's a good example.
I guess this should be.
I don't think. Yeah, I'd say give it a little bit more of a step. Go from 0 to 2. That's enough to see. So in this case, what do you think's happening as you go further to the right? So as A gets bigger or smaller, what do you see happening really?
I mean, we've got like a range here where it's not, where it's kind of converging to zero after a while.
Yeah, you're concerned of how it's looking as, the red line moves to the right,
Right.
right? That's what you're concerned with, like where that's going. So what do you think?
It seems to
So
be
as you've
kind
gone
of,
above one, it's changed, right? As well.
yes, right above one, it's like just exponentially goes to infinity.
And as you go below zero, it looks like it's going towards zero, right? I mean, as you go below one, it looks like it's tending towards zero.
Right. Yeah, yeah, yeah.
So this is the kind of problem that's what your problem is trying to explain. What's happening here? What's happening as you shift, below one, then above one?
Yes. Yeah. Okay. And
So that's the idea, right?
yeah.
And so that hopefully gives you a little bit of intuition about what you're seeing, right?
Right.
Um,
And
so yeah,
then
when we go to the problem,
mhm.
so convergence is easy, right? When I say easy, as in you understand what it's asking you to do in terms of you're trying to match the definition to the sequence, right? You're trying to show that the sequence satisfies the definition.
Yes, but I mean, I think I still need to build a lot of that intuition because there's just a lot of variables going on with the definition of convergence.
100%.
Yeah.
Yeah, and that just, hopefully it comes with time, like you can kind of see what's going on. With this problem, is this like your first is this like a homework sheet or is this like a problem set? Where did you get this from?
Yes, this is a homework problem set. This is assignment two, and the first assignment was pretty much just like piano axioms and properties of real. So this is like the first time I'm facing convergence.
And do you know what the binomial theorem is?
Yes.
Okay, because you would need that a little bit for this problem. So if you start trying to work through it, where do you get to? If you start trying to play around and what do you find you're trying to solve, and then where do you think you're getting stuck?
Well, this time actually, I worked through someone else with someone else on stream a couple times ago,
Hmm.
um, and he suggested kind of taking this definition and plugging in what we're given it converges to, and then trying to work backwards to find a value of big N, I guess, that satisfies this definition. Um,
So what would a n be in this case, right? A n in this case would just be x to the power of n, right?
yep,
Perfect. And then what would your limit be when x is less than 1?
0,
Perfect. So that would be your capital A there, right?
right?
So you're trying to show that the modulus of xn is less than epsilon once you choose n large enough, right?
Yes,
So the goal is then to try and find that large n.
right.
So I'm just trying to keep you like focused on what your goal is in terms of like what's the point of all of it, right?
Yes,
So now obviously I'm trying to give you the answer without giving you the answer,
right.
unless you want the answer. Is that how do you want to do this?
Well, I'm obviously trying to build my intuition as much as possible. So I guess um,
So struggling's quite good then.
yes, it is quite good. Yeah, but ideally, right, you want to like minimize the amount of it, like min max the struggle's worth. Like I want to struggle, but if I'm like banging my head against the wall for hours, that's obviously not efficient. Um,
Yeah, I mean, I'll give you a little hint then.
yeah,
So if we know x is less than 1, what
yeah.
can we kind of say about 1 over x? Do you use a pen and paper, by the way? You'll find it a lot easier to write things down, and I
I
don't
do.
know.
Yeah.
Yeah,
Um, I might have to change something about my stream really quick.
or if you want, I have I can do the writing for you, but obviously that's worse for you. It's up to you how you want to do it. And then I
Hmm.
can screen share. I have my thing connected to OneNote.
Yeah, I think let's do that for now, because my stream setup isn't
Okay,
Perfect.
if you just give me a minute to kind of
Yeah, sure.
stuff around. Okay, let me check that this is all working. The only thing is, obviously, with me writing, it might make it harder for you to. And also, my writing's not great either. I don't write anymore after graduating. So.
That's interesting. Do you do all your math like on
Oh, I do like just scratchpad writing, so it's very
right.
messy, kind of.
Right.
It doesn't look pretty at all. Okay, let me try and share screen. Let me know when you can see it. Yeah, how
Yes.
does the screen share look?
Looks good.
Okay, let me try and start writing a little bit, see if... Actually, let me do... Let me zoom in more, actually. Let's check this. Yeah, okay, we're good. Okay. So yeah, I mean, at the moment, we're trying to show this, right? If an is equal to x to the power of n, and the absolute value of x is less than 1, then this shows that an tends to 0, right?
Right. Yes.
And the definition, so now we need to just understand what we're trying to show. So what does this mean here? This means that for any epsilon greater than, by the way, sorry, for any epsilon greater than 0, there is, do you know what I mean by natural number, by the way, and like when I say real numbers
Yeah. Yeah.
and things like that? Perfect, okay. There is a natural number. Is it called capital N again?
Yes.
Yep. Such that, then we're going to say, we want an, actually, you know what, let me just make it easy as possible. Let's just do this. Such that xn is less than epsilon, right?
Yes.
So what I did was, rather than doing that step of us substituting in for an, I just skipped it,
Yeah.
just to make it easier.
Mm-hmm.
So just to double check, we're saying that for any real number epsilon greater than 0, we can find this natural number n, which is like our goal. That's what we're aiming for,
Yep.
such that xn is less than epsilon. Now, the one trick I'll give you start is, if we know x, let's just say x is positive, just to make that even simpler,
Yeah.
less than 1, then what can we say about 1 over x? What can we say about that?
It's greater than 1.
Yeah, you're right. And so if that's greater than 1,
Yeah.
we can actually then just say 1 over x is equal to 1 plus some very tiny positive number, or like some positive number, right? So we say h is greater than 0. Do you see that trick?
Yeah, sure. Yeah.
Right? So if to give you an example, let's say x is... Do you see it easily, or is it still like a bit fuzzy as to why it works?
I see that easily. I'm just confused on where you're going with it.
Yeah. So do you remember earlier I mentioned the binomial theorem
Yes.
as well? Do you
Yeah.
remember that?
The
So,
expansion of a. Yeah.
yeah, exactly. So on, right? Um, okay, so
Yes.
can you see any way that I'm trying to not give you the answer explicitly, right? So can you see any way some things are matching up, somewhere?
I mean that right side somewhat resembles an expansion of a binomial theorem, but
Have a think. Obviously, you don't have to get the answer straight away.
yeah.
Once you've seen this trick, by the way, the question becomes a lot simpler.
Hmm.
So that's why I'm a bit hesitant on just outright, giving you that answer.
Yeah. Yeah.
You know what I'll do as well? I'll make it a bit easier. Just to make it, let's call this, I don't know what's usually a k, right? That's the normal way it looks.
Are you allowed to treat that on the right side as 1 plus h just to the power of n and then expand?
That's a good idea, right? You've recognized that the 1 plus h here is matching this. So let's see if we chuck them in together.
Mm-hmm.
You've got 1 plus h to the power of n is equal to 1 plus nh plus whatever, right?
Sure. Yeah.
But how does this help you? It's a good spot and it's right, just to give you a bit of a push that you're going in the right direction.
Yeah.
But again, you need to find a way now that it helps you.
Yeah. And in this case, n is just 1, right? I mean,
No, n can be anything.
oh,
N is just a natural number. I didn't write this definition out properly, by the way.
yeah.
Whenever n is greater than n, sorry. So that's what n is. N is just any natural number. Just think of it as a natural number for now. You're just playing around with it, trying to figure out, some patterns that you can then exploit to kind of, show the convergence holds. That's the general strategy, right?
Gotcha.
So you're playing right now, trying to figure out what you're looking at.
And again, what are we trying to...
Yeah, so...
What's the desired outcome?
Well, we want to show... I'll do a little bit of a jump for you.
Yeah.
xn is less than epsilon.
Right.
So we want to be able to show that we can pick this little n so big that this value here is less than the epsilon. So I'll do a little bit for you. We know xn is equal to 1 over 1 plus h to the power of n. Does that jump help a little bit?
1 plus 1 over h to the power of n.
And then you would just show, if you can show that this, is less than epsilon. By the way, my h looks really bad, sorry. If you can show that, you've basically shown the convergence, right?
Why do we have 1 plus 1 over h is equal to x
here,
to the n?
You see here?
Yeah.
You just take the reciprocal of both sides again, right?
Gotcha.
So if 1 over x is equal to 1 plus h,
yeah,
then x is equal to 1 over 1 plus h.
I see.
Do you follow that?
It does. And then, you just exponentiate. So okay. Yeah.
So this step is the crucial one. This step here is one crucial step, showing that equivalence. And this step here is the other crucial step, where you are going to use this so that you can choose n such that it's less than the epsilon.
And can you choose n in terms of epsilon?
Yeah, you can, but you'll see that you won't need to. It'll be easier than that. You'll see you won't need to really be worried too much about that.
And we know epsilon is greater than or equal to 0, so if we show that that term just is 0...
I think the easiest way, ignore epsilon for now, and just think about how you can squeeze xn to 0. How could you force that to go as close to 0 as you wanted it to? I'd say, what would you need to do to kind of make it squeeze to 0?
I mean,
think of it a bit more intuitively than the epsilon. I think that would be easier.
If n is tending towards infinity, right, the bottom would just become a really huge...
I'll give you another hint, which will help. Do you know what the rest of these terms look like?
They've got...
So I've done 1 plus nh plus... What would the next ones look like?
There's a choose term, and then...
we can do that. We can do it that way. So that would be n choose 0, n choose 1, n choose 2.
Yeah.
And then it's h2, right? And then so on.
Yep, up to hn.
So what can you say about those values? Are they positive or negative?
Well, h is very small. They're all positive,
right?
though. Yeah.
And these values here, n choose 2 and so on, they're positive as well, right?
Yep.
So you can say that this is all positive, no?
Mm-hmm.
So if you know that remaining term is positive, if I wrote this, how would you feel? Check. if I wrote that, how would you feel about that? Does that make sense or no?
Is less than or equal to?
It's greater than or equal to, sorry. Yeah, right. So 1 plus h to the power of n is greater than or equal to 1 plus nh.
Yeah. Yeah, because that's
You
just
see
like
it?
a subsequence of the full.
Not necessarily it's a subsequence, but what you're adding on here is positive, right? So it
Yeah.
only makes the number bigger. So if you stop adding those, if you stop adding that part that's making it bigger, you're back to a smaller number, right?
Yes.
If that, just make sure these things make sense, because once you see the steps, then everything becomes quite easy
Mm-hmm.
to the point where it's trivial almost. It's literally that once you make those leaps, there's only 2 or 3 leaps you need to make,
Yeah.
then it becomes easier. So
Okay.
now we've been taking reciprocals of everything, and
Yeah.
this looks, we got something quite similar, right? We got this. Wait, let's use this color. We've got this part here that we're concerned with, and we've got this part here that we're concerned with, and we have an equality here, and we have another inequality here, right? So we've got quite a few things that are matching up, but they're just the wrong way, right?
Right.
We want to show that this is less than this, but right now we've shown that this is greater than this.
Mm-hmm.
So do you know a trick to kind of reverse the equalities around?
I
We
mean,
want we want to flip this around, right? So
yeah. I mean, you could negate everything, I guess.
not necessarily the gate, but what would happen if you take the reciprocal of everything?
Would you get a inequality flip?
When I say an equality flip, it's a bit of an intuitive way I'm saying it, but
Yeah.
we want to flip this around, right? So let's just do it. I'll do this step for you as well. 1 plus h to the power of n, 1 over 1 plus nh. So which way would the inequality be?
It would be. I mean, wouldn't it be the same way?
Have a think about it. What's happening
Oh,
when
you're
we take the
multiplying
reciprocal?
by the reciprocal. Yeah, it would flip. Okay.
Yes, imagine it this way as well. You're dividing both sides by 1 over n. So
Right.
easiest way to think about it actually would be to do it this way.
Yeah. I
So we
see. I
divide the
see.
left-hand side by 1 plus h of n, and then we divide both sides as well by 1 plus 1 plus nh. So we flipped it around.
Right.
And you see now a little trick we can do here. We have this here, we have this here.
Yes.
Do you see a trick or a substitution we can make?
You can substitute it in, but won't it change the inequality?
It will, and that's perfect. That's
Yeah.
what we want, right? So let's write it down here, so we
Yeah.
keep it. By the way, this is, when I say I don't write, this is why it looks so messy right now. I do a lot of stuff just scattered around wherever it makes sense.
Yeah,
So
I do
I
that too.
apologize for it beforehand, you know.
Yeah.
So we got 1 over 1 plus h to the power of n, right? So that's this going here,
Yeah.
and we also have that going in the exact same spot.
Right.
And we know that's less than or equal to 1 plus nh. And now this part's the easy part. We know that as n tends to infinity, what's going to happen to this?
It'll go to zero. The whole.
Exactly, and
The
that's
whole
quite,
quantity.
you see how trivial that is, right? It's a,
Right.
you can imagine as a number goes up by 1 in the bottom, like the entire thing is just going to tend to 0. The denominator is going to get so big, it tends to 0.
Gotcha. Yeah.
And
Okay.
that's, do you see how that's solved everything?
Yeah. That is actually quite simple.
It's just these, the reason why I was a bit hesitant on, or I tried to kind of give you a little push here and there,
Yeah.
is because your big steps really, you need to recognize that you can do this trick,
Yeah.
right? You rearrange the problem into a simpler problem. You need to recall the binomial, and then after that, all you're doing is you're bringing parts together, right?
Right.
A little bit of pain here,
Yeah.
but yeah, you've basically shown what you need to show. So once I think, and then once somebody can understand this part,
Yeah.
putting it back into this definition here, putting it like the entire argument back into this definition, where you're saying this, that's the
Yeah.
easiest part.
Right.
The hard part is getting this whole,
Yeah. Yeah.
this wrapped around in your mind.
Yeah, it is. I haven't seen like binomial theorem used in that way ever, but it
There
makes
are,
sense to me. It's just an interesting algebra maneuver.
yeah, I mean, there are other proofs. I
Yeah.
know, I think I saw in that sheet you had up earlier, I saw a proof with log. Someone used a logarithm.
Yeah.
I prefer this proof because one, the log is actually quite difficult to define.
Hmm.
Um, some people define it, so if you look for an actual definition,
Yeah.
some people define it as the inverse of an exponential. Some people define it as like the integral of like 1 over, I can't remember how they define it. There's an integral that you can define it as, which actually makes the most sense. But if you use this argument, all you need is the binomial theorem,
Yeah.
and that's a simple counting argument from discrete maths, right? It's just simple counting to prove it, so it doesn't require any, you don't have to depend on anybody else's, or it's a very simple level,
Right.
right?
It yeah.
Where you
It's
haven't
kind of
used any,
weird to define or try to prove something about a limit using something based on an integral, I guess.
yeah, which is itself a limit, which is the
Yeah.
funny part. So, but that works. But the thing is, that proof
Yeah.
would work as well with log. So
Yeah.
it's a bit of a personal, taste.
Um,
But yeah,
so how do you go about proving this the other way when you're trying to prove something diverges? Are you trying to show like
let me stop sharing screen for a second because I want to see if I can find. I'm hoping to find a nice Wikipedia link
yeah,
that will uh, that will give you the idea. So
right.
there is generally there is a way to kind of negate statements in mathematics. It is an algorithm, so it's quite easy to do.
Yeah.
Let me see
There's
if I
just
can
like a
find a
ton
symbol
of
and send it to you.
quantifiers in front of this
Yeah,
definition.
the problem with using English to negate a statement is that our English it messes up on quite a few points. So um, I can't think of any examples on top of my head, but there's a reason why I even refer to the algorithm and I try to be as intuitive as possible.
Yeah.
Negating mathematical statements. Wikipedia is quite nice with this.
Hmm.
This is something that would probably take. It would probably be a bit of time to wrap your head around. So I hope you are now.
Yeah.
But that's the general process. You would take statements and then you would give the negation. Once you can do it, it's quite easy. But to build up that kind of yeah, it's quite hard to build that intuition in terms of negation. It's not normal, and it's not intuitive.
Yeah.
If you've seen the link.
Hmm. Yeah.
So
University
I'd
of
say
Toronto. Hmm.
refer to this, give it a little skim right now, but then have a reference to it, and then you'll memorize the tricks.
Right.
They just
Yeah. And a lot of like De Morgan's law.
yeah. De Morgan's law is essentially the main trick to do a negation,
Yeah.
but they give you some English examples as well where English matches up and where it doesn't. So I've just done a little skim and it looks good.
Yeah. Man, the chat is like mind blown about your binomial theorem trick on that.
I think I learned from a different textbook. So the textbook I learned from, I saw the trick first.
Yeah.
So once you've seen the trick, you can imagine how easy it is to remember, right?
Yeah. Yeah.
It's like you know when you're writing code or you're using a language, you don't know every single function, or there might be some functions that are better than others, or
Right.
methods of like an object that's already been defined for you, right?
Yeah.
But once you know the method and you find out how useful it is, you won't really forget it, right? It's the same kind of concept.
Right. Yeah. That makes sense. Um
But yeah,
and
so I'll help you around with the negation because it's not as trivial. But we don't need I'm wondering if I should give the formal definition or if we should use a different one. You know what? I think let's use an I know you have to, in maths is about being rigorous,
Yeah.
but do you mind if we go for it first in like an intuitive way
Yeah, yeah,
in
yeah.
terms of making that make sense?
Yeah.
And then afterwards, I promise you, once you get like a little bit of experience, um, once you can build these kind of intuitive arguments, the game you're playing afterwards is about just matching that simple game as a child, you match the triangle, shape to the triangle hole, and
Sure.
that's all the definition of matching is, I promise.
Yeah. Yeah.
Let me share screen again, and let me know when you can see it. Is it showing up on Discord now?
Yes, it is.
Perfect. So what we're trying to show now is just going to do it a little bit easier because it's easier to think about. And then the generalization is much easier. So we've shown this case, right? X is here.
Yep.
Now we're going to do this other case where X, by the way, do you guys write one? I don't know how you write one in the States. Do you write it like that, right?
Yeah, I mean, I kind of write it like an I.
Yeah, so we want to show this case, right? So if X is greater than 1, we want to show, actually, yeah, let's just use some symbols, that X to the power of N tends to infinity. This hasn't been defined for you yet, but we're going to say that this is going to say it diverges. So what do we mean by this statement? Well, we're trying to say for any we can find, so this is, a lot of maths is building the definitions you need to use. So right now I'm building a definition of what divergence looks like.
Yep.
There is a formal way to negate the convergence definition. So it doesn't match, but you have an intuitive argument for where then you can make it match. So for any real number m,
Yeah.
we can find this natural number n, same capital number n, such that xn is greater than m whenever n is greater than n. So does this make sense first? What I've written here. I know you haven't seen this definition before, but intuitively, does it make sense as to why if something did this, it would tend to infinity?
Yes, it does. It's basically just, I mean, it's kind of you're just flipping and making exclusive.
And also you can refer back to that Desmos graph as well, right? In terms of playing around with it. Essentially the graph will look something like this, right? And the main point I'm making is no matter which point you pick here.
Oh, yes, yeah.
I can go to the right, I can keep going to the right, and I can find you this value, which will be n.
Right.
Right? And then what I'm saying is I found this n, which is here. And then what I'm saying is if you pick any n, small n, somewhere here, and that would match to the point here, which would be x to the power of n, right?
Yeah.
We know for sure that it's greater than this value m. That's what this definition is really saying.
Right.
Right?
Yeah.
Now, the reason why I'm using this definition is because, again, I like using the easiest possible way to kind of approach the problem, and then afterwards you're just playing like a translation game.
Right.
So we're at this situation now where you can see that you have this x to the power of n over m. I mean, it's greater than m, sorry. Have a think, because it's a very similar trick. So have a think about what the tricks we used before. Or what tricks do you remember from before, and I'll tell you if they're relevant or not.
I mean, we have the binomial theorem expansion. If we can rearrange that.
That would be useful.
Yeah.
That would be useful, yeah. So keep that in the back of your mind.
Okay.
All right, here as well.
Yeah.
Binomial expansion there. What other trick did we use?
There were like 3.
Let me scroll back as well, just to give you a bit more of a hint.
Right.
It's one of the other ones I like.
Are you talking about the fact that we can represent one over, like the reciprocal of x as a small um, nudge above 1? I consider that kind of the same trick.
Yeah, think about that trick though and how it applies here. So how did it work here? Why did we take that reciprocal? Because we need the number to be greater than 1,
Yeah,
because we want to add a positive number to it.
right.
So if you have 1 and you add a positive number, it has to be greater than 1.
Yes.
But you already have x is greater than 1 here, so do you need to do the reciprocal here?
No, you don't. You could.
So how would you feel about if I wrote this? Sorry, h, where h is greater than 0. How would you feel about that? Does that make sense
That's
to you?
reasonable, yeah.
Yeah?
Yeah, sure.
Okay, so let's play that trick again. So we did what we did before.
Yeah.
We have x to the power of n equals 1 plus h to the power of n. And that's equal to, if you remember the binomial theorem.
Yep. And then we get.
So I'll write like stuff like the binomial theorem out because it doesn't really matter too much if you remember it or not in detail. I don't even bother writing them all out. But so we're here now.
Yeah.
And what was the other trick that we used?
Well, we can take.
Smaller steps.
We can take like the first two terms and say that since the rest of the terms are positive, we can kind of create an inequality using them.
That's perfect. That's exactly it. So you have 1 plus nh.
Yeah.
And is the equality the right way around? What do you think?
Um,
Shall I put it? I'll put it next to it so it's easier to see as well. Sorry.
yeah. Since that
Think about
whole
it this way as
section.
well. If you have a number 1 plus a number 2 plus a number 3,
Yeah.
would you say that's greater than equal to, which way would the inequality be in this case?
It would be towards the side of the 3, of course.
So is it this way, right? Or the other way?
Yeah. Yeah. That way. Yeah.
Perfect. So can you kind of play that matching game with what's here? Think about it the same way. And that would show you why it's a bit,
Right.
The first time I saw it, it took me a minute to get comfortable with why it makes sense.
Yeah.
Even though it is right, it's just, it's one of the things that you kind of have to kind of struggle with for a second, make sure you fully understand it, then you can move
Yeah.
on.
It's a little weird that you're kind of using like not all of the elements. Like you're getting rid of some of the elements in the full expansion in order to create this
Exactly.
inequality.
Yeah.
Yeah.
It's just, it's one of those things that it's good as well to get your head wrapped around it at like this point, because
Right.
it's a trick that's used very often.
Yeah.
Especially for this type of problem. I should have done all of it, by the way.
I guess one thing I'm wondering about this is like, does this hold up at the extreme edge case if n is like 0 or 1? Because then you don't have access to the full.
Yeah, so I am being quite, I am skating around that.
Yeah.
With limits, the main thing is you're never worried about what's happening in the finite, or in these finite cases.
Right. That makes sense.
So with limits, you don't really care what's happening at n is equal to 0 or at n equal to 100 billion, million, thousand, or you don't care what's happening at these specific values.
Right.
You just care what happens as n gets to a number that you can't even count to, that gets to infinity essentially.
Yeah. That's the programmer in me just checking the for loop.
Yeah, no, I
Edge
understand.
cases.
You want to
Yeah.
build some test cases and check it works in those test cases. I understand that.
Yeah.
With limits, I think the main thing is you want to understand the problem you're trying to tackle is not necessarily what's happening in these exact cases, which is why, I told you to plot the graph.
Mm-hmm.
It's a good idea to have an intuitive idea of what's happening, but you're not really concerned what's happening at any specific point, right?
Right.
Or any fixed value. But yeah,
Yeah.
look, we're at this point here, right? Where, by the way, me picking n and h is probably the worst decision I made. So I need to be okay. That's a clear n and that's a clear h. That's a clear h. So we're here, and we want to show that this term here goes to infinity, right?
Yes.
What can you say about this term that's smaller as n goes to infinity? Or as n gets bigger and bigger? H is positive, by the way, just So don't worry too much about that. But
Okay.
what can you say as n gets bigger and bigger? What can you say about this right hand side?
I mean, that'll go to infinity as well.
Okay, so you found a term. So let me squeeze some of this together to make it easy to see. You've got xn here, and you've got a term that's smaller here. It's a smaller term, right?
Yeah.
And you're showing that this goes to infinity. You know that it's obvious that it goes to infinity, right?
Yeah.
As n goes to infinity, that goes to infinity. But that's a smaller term, so why would the bigger term not also go
Right.
towards infinity?
Yeah.
So
Yeah.
you
Yeah.
have an intuitive idea as to what's happening,
Yeah.
and what you want to show is that xn is bigger than m. So if you know this right-hand side goes to infinity, you need to show that it's bigger than m, right? I'll use
Yes.
this equality for you as well. So that's what you want to show. So sometimes in maths we write something like this, or
Hmm.
yeah, we write something like that. I've seen some place. I don't know. I think that might be a European thing.
Yeah.
But we want to kind of show this
Yeah.
or find this value of n. So I'll do a little bit of maths for you to help you out. We wanna prove this. So all you have to do is just do nh minus 1, and then just a little bit of algebra for you.
Sure.
Nothing crazy happened, right?
Yep.
Okay. So what we said here is, and by the way, I'll be a bit more formal if you wish. Still not too formal, but we know that n is greater than. So okay, this m, someone's giving you this number, right? Someone's told you, I want you to find n such that this sum here is greater than this m,
Yeah.
right? Let's say I told you I want you to find a little n. I want you to find a value for this little n such that this sum is bigger than 100,
Yeah.
right? So let's just do whatever, right? I will do that.
Yes.
Yeah. So
Right.
that means if you choose, gone. Yeah. If you have any questions.
No. 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 This makes sense.
Oh, perfect.
Yeah.
So if you choose, if let's say h was 1, right?
Yeah.
Just for an example, that means if you choose n is equal to 100,
Yeah.
what can you say about this inequality? Put this one here. What can you say about that? Does it hold for sure if n is 100?
I mean, yeah, because you've got that extra one.
Okay. And
Uh,
if you told me instead now, rather than 100, I need to find a number bigger than, I need to find n such that it's bigger than 1,000.
yeah.
I could follow through the same idea, right? So now just change that to 1,000.
Right.
I change that to 1,000. Gone.
Yeah. So you can just generalize it to a variable.
Exactly. So we have a process, right? But let's make this back to its general m.
Yeah.
I think I saw in the last stream he tried to explain it to you as well in terms of for all, as in someone's giving you something or giving you a number, then you have to find it. So that's essentially what we're doing, right? So we've given a general. Don't need this actually.
Right.
And we
Yeah.
don't
Yeah.
need
Yeah.
that.
A variable and for all seem to kind of be pretty similar.
Yeah. Again, it's easy to kind of say, but for me to obviously just tell you what like for all means, but it's more of a when you struggle enough, you'll get an idea of the mistakes and what for all means and how to kind of think about certain things.
Yeah.
It's a bit more like maturity, right? Building that
Right.
up. But yeah, so essentially what I've said is if we set this to equal to n, if you remember from here, for any real number m, we
Yeah.
can find this capital N such that this inequality holds whenever that's bigger than that.
Yeah.
We know that if we set this to be n, this value here, right?
Yeah.
If n is bigger than n, then that means 1 plus nh is bigger than m, right? Do you see?
Sure. Substitution. Yeah.
Okay. And then you know from this part that you can just... Oh, by the way, don't build this habit. This is a bad habit of chaining implication onto implication. So don't build that habit. But yeah, if we're taking this inequality here, and we're going to chuck it in front, right?
Yes. Okay.
And now we're just going to get rid of this middle part,
Right.
right? Which is the same thing as just xn. Can you see the bottom of the screen, by the way?
Yeah, I can. Yeah.
Yep. You know what? I got some of these messed up. Sorry about that.
Yeah.
It doesn't matter, by the way. You can do it either with a strict inequality or not, but because I defined it earlier with a strict inequality, I'll keep it the same.
Why does
But
that
look,
not matter? Is it because it diverges, so it's kind of it's
yeah,
all
so like,
arbitrary?
uh, let me get through this part first, and then I'll show you why. It's quite an easy one when you see it.
Yeah.
So look, we were looking for this,
Yep.
and down here we have it.
Right.
So we found this n. We found the capital N, which we've set to this, right?
Yes.
So we set that to be the capital N. Then we know that whenever that little n is bigger than the capital N, we have what we're looking for.
Right. Yeah.
So intuitively, we understand it here, right?
Yes.
Intuitively, we know that xn is bigger than this smaller term, and this smaller term shoots off to infinity. So xn must also shoot off to infinity, right?
Yeah.
And that's for us to kind of understand and be able to kind of, we know the problem is probably correct. Let's formalize it now.
Right.
And then all this other part is just formalizing. All
Yeah.
we've done here in these little steps is just put it into a formal statement.
Right. Yeah. So I guess the algebra is pretty simple. It's just like what substitutions are you allowed to make with the inequalities that takes a little bit of practice.
Yeah, it's all just building that maturity,
Yeah.
playing around with it. Now, after this conversation, hopefully you'll remember this little trick here where you can sub in, you can do that little trick with the h, right? Or
Yeah. Yeah.
if it's not greater than 1, you can take the reciprocal and then do the trick. And then
Right.
when you're seeing something to the power of n and it's an integer, maybe it'll make you think a bit more about the binomial theorem.
Yeah.
Things
That is a
that
very
build your maturity.
powerful trick.
Yeah, but that's essentially those two problems done. Um, the only part that's a bit off, to be fair, with the
Yeah.
problem is this definition here. So I used a bit more of an easy definition just to help you with your intuition.
Yeah.
The trick to do negations is whenever you see a for all, you turn it into a there exists.
Yeah.
Whenever you see a there exists, you turn it into a for all.
Sure.
Do you know these symbols, by the way?
Yeah. Yeah. Yeah.
Have it. Okay. So the formal definition of a convergence is for all epsilon greater than 0, there exists n, which is a natural number. Let's just use this, such that n greater than n implies mod. So we're saying an approaches a. Is that the that's the one, right? So an
Yeah.
minus a. So that's an epsilon, and we should probably put a little bit of brackets around certain things, right?
Yep.
So to negate it, we're going to switch this around to the there exists. It's not. It's a bit. Yeah, you'll see why it's a bit finicky. And why I don't like using it, but it does work.
Yeah.
Such that. So wait, let me just make sure. Even I'm uncomfortable with it.
Yeah, the
All epsilon
negation
greater than
of
0.
implication is. Oh.
There
I
is a
see.
formal negation of it, but to do it this way, I'd say it's a bit more easy to actually write a different way. So wait, just to double check. So for all epsilon greater than 0, there exists a natural number. There exists epsilon greater than such all natural numbers. Okay, so we need to negate this part inside here now. So
Yeah.
to negate that, what we're trying to show is there exists an n greater than n such that an minus a is greater than or equal to epsilon. That's the negation of convergence, this one here. I'll highlight it for you. So that's the negation of convergence, and
Yes.
the one on top is convergence. It just doesn't look nice. It's hard for a normal person to kind of wrap their head around. So I don't
Yeah.
use it. But some people obviously don't mind using it, which is why it exists probably. But yeah, I mean, you see how you feel about that statement. It makes me a bit uncomfortable, so I don't use it.
Yeah, it does. Just trying to digest all the quantifiers is kind of.
Intuitively, you can make an intuitive sense of the statement. It
Yeah.
just isn't comfortable to look at. The intuitive idea is actually it's a bit hard to kind of understand an intuitive idea without having a strong understanding of convergence, which you still need to kind of work on. But
Yeah.
the main point is we can argue against this. That's what's happening. This is just arguing that this is not true. right? So let me try and think of an example for you. If we do, I can't think of an easy one to look at. Sorry.
For
Can't think of.
convergence.
No, for divergence, like an easy one to understand,
Hmm.
and then to be able to kind of put the definition on.
Someone in the chat
See if
might know.
I'll try, because I'm trying to think of an easy one where you can easily see how it breaks. The easiest one I know is -1 plus 1. So you have a sequence of -1. I'll write it down for you, but I just don't see it. It's not like too good. So you have, this is your sequence, right? You start at -1, then you go to +1, then you go to -1, then you go to +1. Do you see how that's a sequence, right? In terms
Sure.
of
Yeah.
it should
Negative
be
1 to the n. Yeah.
yeah, -1 to the n plus 1.
Yes.
Because we're starting at the -1, and
Right.
it depends where you start n at, so it doesn't matter really. But you see it.
Yeah.
In terms of what this looks like, so -1 plus 1 -1 plus 1 -1, so on. The way that this convergence, this hair fits in, is if I choose epsilon to be 1,
Yeah.
and I choose a to be 0, right? So
Okay.
this is like your graph. It's a badly drawn graph, but okay. Here's your -1 value, and here's your +1 value. So it starts at -1, then goes to +1, -1 plus 1, -1 plus 1. I can find an epsilon, so that's there exists. So I've matched that.
Yeah.
I've found an epsilon, or there exists one, which I've
Yeah.
set to be equal to 1. So I found you like a concrete example, where it doesn't matter which value of n you choose. The distance between these 2 points, let me use a different color. The distance between -1 and +1 is always going to be greater than the epsilon, right? So that's always going to be 2. This blue line,
Yes.
you're going 1 up and 1 down, so that's distance of 2.
Yeah.
Epsilon is a distance of 1. So we found a case where that distance will never get closer than epsilon, which is what this is saying. We can find a distance epsilon such that the distance between the sequence and the limit is never closer.
Okay. Yeah.
Obviously, there's a little trick here, but the
Yeah.
main point is it's not, even intuitively, it doesn't really help.
But it's bounded by it. You can always find a greater a point further along where that will violate that distance. Is what you're saying?
Yeah, that's perfectly it. So
Yeah.
in terms of reading the statement, you've understood the statement, right? It's just for me, I found it quite difficult to kind of understand it intuitively.
Yeah.
But yeah, that's perfectly it. You can always find that natural number n such that you violate the distance. Even I remember the last time with the call, he gave a good intuitive explanation of what convergence is, right?
Yeah.
The way that he explained it was, which is how most people would explain it. You have like a function, right?
Mm-hmm.
Let's say it looks like this, and then you have a value that you're saying it's converging to. Let's say it's this one, right?
Yeah.
Epsilon is just how far away you are. So if I say I don't want to be too far away, the most I can tolerate is this distance from the red line,
Hmm.
the black line between the red line.
Yeah.
Then as long as you're past this point here, you're always within that error kind of, you're in that error or the tolerated error, right? So that's the
Right.
kind of normal explanation I think people give of limits, which is also quite intuitive as well. But yeah, I mean, I guess it's kind of one of those things where you'll play around with these problems, and you'll build your own, what you prefer, right?
Right. Yeah. Yeah. Yeah.
But
But
yeah, let me know what you're thinking. How do you feel about that problem? How do you feel about convergence?
I'm just still blown away by your binomial theorem trick. I would not
Yeah,
have
you'll
thought to
see.
do that.
Yeah, no, because I've seen it before, it's very easy for me to obviously then to say it back to you. Um, I think when I did it first, I got quite lucky, but I think when they showed it to me, there was a previous problem which was quite similar, so it
Mm-hmm.
built up in steps. Whereas obviously this is the first time you're kind of looking at the problem that needs the binomial theorem in that way, right? So it's a bit more of a bigger leap for you than it was for me, because I
Yes.
think my lecturer had given me a couple steps in between in some of the previous problem sets. If you remember, I asked how were your other problem sets, and you said there was one, but it was more about the piano axioms, right?
Yeah.
Which, to be honest, you're probably better than me at now. I haven't used those axioms. I haven't looked at those axioms.
Yeah. Well. Yeah.
There's a new, more modern version. If you want to have a look, it's called ETCS, which I've had a quick skim through. But let me see if I
Yeah.
can send you a
Et.
link for it. I'll give you the actual set theory. And it's Tom something. I'll have to remember. Okay, it's a free PDF. Yeah, if you just go, I don't want to send you a link to a PDF so I can find your credit card or whatever. So I'll just send you if you Google that, you'll
Yeah.
find it. It'll be the first thing that pops up. Axiomatic set theory. It's a different approach. It's a bit more modern than the piano axioms, but it essentially covers the same thing. So whatever you can prove in the piano axioms, you can prove in yeah, you can prove using ETCS.
Axiomatic set theory. Okay. Yeah. Yeah. It's really interesting how math is changing still. It's
Yeah.
like, I don't know. Before I started this, I was under the impression it's kind of a stagnated field, but not at all. It's work done all the
Yeah,
time.
it depends. You can always make something, you know, you can always reinvent the wheel. It doesn't really add anything. It's just an easier way to think about the axioms, approaching it this way, right?
Yeah.
There are certain parts of maths that are obviously still the same and will be the same for the rest of our lives at least.
Yeah. Yeah.
Yeah. Have you ever heard of category theory?
Yes, I have. Yeah, from this
Perfect.
channel Oliver Lug. I don't know
Yeah.
if you've heard of him.
The YouTube videos I can never understand.
Yeah.
But this person here, Tom, he works at a uni, and I worked with him for a bit. He's a specialist in category theory, and what he's done here is he's essentially mapped that onto logic and onto the axioms, and it's it's quite interesting.
Yeah. Yeah. It gets quite meta though.
I think his approach. So in this, he teaches this course to a bachelor's
Yeah.
course, which is
Oh wow.
a second year or a third year. So it's actually anybody can kind of pick it up really and read it. You don't need you don't need any techniques. I mean, he's talking about sets and functions between sets, and that's it.
Right.
He doesn't even explicitly say what a function or a set is.
Yeah.
But anybody can pick this up. It doesn't have any prerequisites or nothing, and it's quite interesting. And also, it builds a lot of your proof kind of skills, right?
Yeah.
Yeah, whenever I watch a video on YouTube about category theory, I get lost about 5 minutes into it.
Yeah. Yeah.
But with a text, this is significantly easier.
Yeah. Yeah. That's really so. You still follow the development of math, like
Just some
outside of your
parts.
job.
Yeah, I mean, maths is one of the subjects where people nowadays are trying to make it more complicated than it is,
Hmm.
and it's just really difficult to follow nowadays. Category
Hmm.
theory, I had to put a lot of time in just to kind of catch up to where everybody else is and be able to understand it.
Yeah.
There are other subjects that are just like, I think there's like a saying, it's called like physics envy. It's a saying in some of these subjects where you'll find people try to make their subject look like mathematics almost. And there are just
Yeah.
simpler ways to kind of do things, and people just aren't
Gotcha.
doing it.
Yeah.
I think when something looks complicated, it looks a bit cool, but realistically, it's actually just quite easy. A lot of stuff to do.
Yeah. Yeah. I know that
Yeah,
all
that
too
makes it
well.
difficult.
Yeah.
Yeah, so it makes it difficult to keep up. Um, yeah, I do try to, but it's not easy.
Yeah.
And obviously, there are going to be parts of maths that are actually complicated and are actually difficult to kind of keep up with. But yeah,
Right.
problem 2 looks interesting as well. I can't see it all the way because of your camera.
Oh, yeah.
That one looks quite interesting, and that's another trick there.
Yeah, I think my professor is really trying to put me in the line of fire of some of these more advanced algebra tricks.
I mean, problem 2 is a little bit mischievous. Is that the way he wrote the question out, or is it? Did you make a couple shortcuts when you're writing the question out?
It's just the original.
But yeah, the trick I know requires an assumption then. Yeah, it is.
Yeah, I mean, I would be interested to see, even if it does involve an assumption. That seems like.
I'll do the writing again for stream, but it's interesting how he's written this out. Or are there any other problems you want to take a look at instead? Is there anything?
Not particularly, no. I'm just.
Or if you want a break and you want to just, digest the problem that we just had, that's fine as well.
No, that's all right. That's all right. I'm here to learn. I think like a lot of the. I do a lot of like digesting of stuff off stream too, but getting like a cool explanation of this would be.
Well, without giving you the answer, if an converged to a number, say a, what would you expect an plus 1 to do?
Also converge to a.
So say for example, an is a sequence that you're seeing in problem 2, right?
Yeah.
Let's just suppose it converged, right?
Sure.
And let's just say it converged to a capital A.
Yeah.
So what would you expect an plus 1 and an plus 1 to do as well?
I mean, both also converge, right? They're just converging to the same.
Yeah, because it's just like you're just going one number ahead.
Yeah.
If one sequence is going to converge, the other ones will as well.
Yeah.
So what would happen if you just took the limits of both sides?
You'd both get a.
Yeah, you get a on the left, 2a. So it's an interesting trick he's done, because that would be the normal trick, where you would apply the limit, put it to the left, and then see what a actually meant to be.
Yeah.
Oh, I might have to hop off soon.
Okay. Yeah.
I've got another 2 minutes before I gotta go.
Yeah. Don't worry.
But that's another fun trick.
Yeah.
With this question though, see what happens if you just substitute. So if you fix A1 and A2, what does A3 look like? What does A4 look like? Have a think about that, and I think that will help out with problem 2.
Okay.
A lot of it, promise you, a lot of it is just you play around with numbers, get an intuitive understanding of the problem, and then the rest, like once you can kind of figure out where things are, like you said, there's a lot of letters, a lot of numbers, a lot of different variables that you're juggling around.
Yeah.
So once you get that intuitive idea, that stress becomes easier, and then you can you can fix your mind on what you actually the difficult parts then, right?
Right. Yeah.
But yeah, I mean, this was fun though.
Yeah. Great to have you on.
Hope you enjoyed those 2 little tricks, and
yeah, that was huge.
But yeah, you'll see loads like that. Also, I saw you plan to write. You were thinking of writing a database, right?
Yeah.
I would say have a little like view of the landscape, view of like what's out there, because otherwise it's very easy to write a lot of the small details that don't really matter.
Right.
That would be my one opinion on that. But yeah, if that's something you enjoy doing though as well, there's always a need for that database. So.
Okay. Yeah. Cool.
Yeah.
Yeah.
No, it's good jumping on stream anyways. Hopefully people watching enjoyed it, and hopefully you enjoyed it as well. But yeah.
Yeah. I did a lot. Thank you.
No worries. All right. Well, hopefully I'll catch you on next stream. Otherwise, yeah.
Yeah.
Cheers.
See you around. Yeah. What a guy. Oh, sweet. I also have a trick for showing this. I have to admit it's not my own. Yo, get this guy on stream! Oh my god, that binomial theorem trick blew my mind. don't know how that guy. Yeah. Actually, one sec. I'm gonna go get some food for a sec, but I'll be back in 5 minutes. Take a break briefly. Have you done any epsilon delta proofs for functions in your course at all? No, but ideally I just want to do more problems than the course actually offers me and just get cracked, but be back in 5 minutes. All right, I'll see you guys in a sec.
My people, my people. Let me give Stavros a little bit more light. Oh yeah, direct sunlight, dude. He loves that. What's up, guys? Oh shit, it's so bright. I don't know how Sylvan's doing this. Just sitting here like this. Oh my, how is he seeing anything? What's up, guys? How you doing? You guys being entertained by my presence? Because that's what I'm tasked to do. Yeah, dude, this lighting is insane. I don't know what he's doing, man. I don't know what's going on, but yeah, I was procrastinating doing my own homework, and so I was kind of like tuned into the stream, seeing what was going on. And some of those tricks were actually pretty cool. Real analysis seems interesting. I mean, it seems interesting as like a, you know, for the sake of problem solving. Like, you know, it's like a cool puzzle. You know, maybe you spend some time solving one of the problems, but I wouldn't want to have to like actually dedicate so much time to completing it as homework. Recite Euclid's Elements in Greek? No. Don't even. I'm not really the biggest math guy. I'm a computer science major. I've completed up to linear algebra, but I'm kind of a bot. Guys, I really want like a nice watch. Like if you guys could, you know, maybe pull some strings, you know, donate, gift, maybe gift me. What? Oh yeah, I need that Russian guy back. I need like a oligarch, or you know, I need like somebody, you know, some kind of like a big like whale, like a crypto whale or whatever they're called. I need like somebody to basically. I want a nice watch. Somebody please gift me a nice watch. Garmin. Well, I'm talking about like a mechanical. You know, like my dream watch is an Omega Speedmaster. So if any of you guys have an Omega Speedmaster laying around and you just like, you know, want to send it over, please, that'd be pretty sick. Otherwise, I mean, what other watches am I really interested in? I mean, I love the Patek Philippe Nautilus, like the look of it. It's a beautiful, beautiful watch. But it's just way overpriced. I mean, for a steel watch. What? It's overpriced. 1 of 10 Omega HMU. Alright, please send it. Please. I need. Do science students have deep voice? I don't know what that means. Please. Guys, I need this. My mom is kind of homeless. But yeah, I really I would enjoy a nice watch. Pretty cheap. Yeah. I mean, like the watch that I want, the Omega Speedmaster, like $7,500, $8,000. Like it's totally doable. I mean, like in the next like 5 years or so, I'll probably buy myself one. But it's just a watch that I've wanted for a long time. I really love that watch. But it'd be fire if one of you guys like just wants to, but put this guy in the basement. Yo, shut the fuck up. Yeah, doable. Buy a clock. No. I don't know. Anyway, recently, in the past, like, I don't know, week or so, I kind of like go in and out of being like really into watches, and I was kind of out of it for like multiple months. I wear my watches regularly, but I wasn't like super invested in watching videos or whatever about watches. But recently I've been on my watch kick, so that's why it comes to my mind, and that's why I'm kind of like, please give me a nice watch. Yeah, exactly, dude. On Omega, you can get that like instantly. It's sick. I think like that's how it should be. It is kind of. I don't know. I have mixed feelings about it. I think that there is something kind of cool about the exclusivity of a Patek or the exclusivity of an AP. Like they won't just let you buy within the anyway, it is kind of cool, but at the same time it's like, bro, really, like, you gotta be a douche. Like, you're shelling out like $100,000, you're willing to spend $100,000, but they're like, nah, like, we're not selling it to you, we only sell it to like Jay-Z, bro. But yeah, Casio G-Shock. Yeah, I was actually looking into a steel case Casio G-Shock, and I was like, yo, that's kind of crisp. Like, I kind of want to buy it. It was like $550. And I was like, sheesh, kind of looking good. What course am I in? In which country? Me? I mean, assuming you're. Well, yeah, $550, but it's like semi-luxury G-Shock. It's nice. It's not just like plastic. It's not just rubber. It's like it's not full. I don't know. I think it's pretty slick. But anyway, I'm studying computer science at the University of Vermont in the United States of America. Oh, maybe it is titanium. Is it? I don't know. I just looked at it briefly like the other day, and I was like, yeah, I want to buy that shit. If you want a Rolex, you can get around the wait list. Just pain in the ass to get around it. Yeah. Watching from India, fire.
All right, I gotta hop on this call with this guy. All right, thanks, Jake.
Goodbye, my people.
You were talking about watches the whole time?
Yeah.
There's a lot of watch fans in the audience.
Yeah, gotta love watches.
Oh my god, it's so bright out. Maybe Stavros is getting his sun. Are plants, like, what gender are plants, actually? There we go. That's more reasonable. Alrighty, back to math. Guys, I'm still fucking mind blown from that that binomial trick. Holy shit, was that big brain. But goddamn. What's up, Alex? All right. How do you pronounce this guy's name? Oh, I got kicked off the call. Okay. Did anyone here grow up in an ingredients household? I grew up eating like raw oats and shit and lentils. Oh. Where are my headphones? And chickpeas. I'm a major chickpea fan. Basically, where did I put my headphones? Minimize cost and taste, maximize calories. Where? What? Maybe they're charging. No. I swear I had them right here. What happened to my headphones? I was talking to the guy and then I took them off. What's up, Soham? Man, I'm confused as hell. Where are they? There's gonna be feedback, I'm pretty sure, if I do this call. Oh, I was about to pull up Find My and dox myself. Under the bed. Good guess, good guess. What the fuck? All right. Should connect to them momentarily. So, they're not even connecting. The Discord link is hard to come by. Where is this goddamn set of AirPods? This is outrageous. I literally... Like, where could they have gone? Oh, there they are. They didn't even connect. Okay. What pills did I just pop? Perk 30s. And some MDMA. Molly. Ecstasy. I'm about to tweak on this math stream. Alright. Let's give this guy a call. Looking back at stream. Looks like you took them with you. That's next level reconnaissance. Hey, how's it going?
I'm good. How are you, man?
Good, good. Looking back at the stream is next level. I appreciate that.
Yeah, yeah, no worries. Damn, I just heard the other guy and his microphone and his voice. It's all so nice and soothing. And then I come with like crappy headphones here. Oh, yeah, it's different.
I don't mind.
Oh, by the way, my Discord username is supposed to say like Johnny, but in a really weird like phonetic spelling in my main language.
I was
That's what
wondering
it is.
that because all of those letters kind of seem like they blend into the same thing.
Yeah, fair enough. It's just I always use like for username in lots of places because it will never be taken. So it's like the easiest thing to remember. That's always the same thing.
That makes sense. Yeah, yeah. Um, did you that binomial expansion trick really was blew my mind. I did not think of doing that.
Yeah, that was great. It's I mean, maybe not exactly like that, but there is a common trick in real analysis, which is like, well, based on that more or less, which is like really, really useful. So I'm glad he brought it up. I think it's like, I think I also said it in chat, but it's like this one inequality that really helps you like estimate like exponential things really nicely.
Yeah.
And this binomial thing is kind of implicit to it. Because I thought like you had this, right? You open this document where you want to write things down from real analysis. I think it would be a nice thing to add there, this inequality also.
Yeah. Yeah. I think. Oh, you mean adding it to like a document of common.
Yeah, I mean, or I guess your document that you made was like more for definitions, but I think also like common strategies or something could also go in there. I don't know, might be nice.
That is a good idea actually, and I can just throw that into like my GitHub, and people can contribute to it as well, which I think would be
Yeah,
probably useful. Yeah.
yeah. I mean, letting everyone do it might be a bit chaotic, but I mean, I get the idea. It's a nice sentiment.
Yeah.
Yeah,
Um, yeah. That definition of convergence is a little weird, but um, I don't know. I'll formalize
yeah,
this later, but
yeah. It's really like you said, it's a getting used to thing, and like this epsilon delta definition of convergence. It's so many quantifiers. Like this algorithm that he talked about for negating mathematical statements with quantifiers is quite useful.
yeah. Okay. Sweet. Um, are you down to like reason through this problem too? I think
Yeah,
like
yeah.
yeah,
Um,
it would be nice
yeah,
to
I
get
looked at it
paper.
for. Yeah, paper is always nice. I looked at it um, for a second, and then I didn't immediately uh, come up with something on my own. So I kind of cheated. Like I have to admit, like the way I did it is not my own idea
Yeah.
entirely, but it's a nice trick. Yeah, I think it's worth showing.
Okay. Yeah. Yeah. Um. Hmm. I'm trying to get my like overhead camera working. It is not working though. Sometimes this continuity camera stuff just never pans out. Hmm. Yeah. What? Yeah. I might just have to type this, unfortunately.
Fair enough. I can also, well, if you want, I can also share my screen. I'm on a tablet. I could like write. It won't be as pretty as the other guy, but
Yeah.
I don't know.
Sure.
I don't know, because maybe you also want to have it like for yourself. So you just have to say what you prefer.
I mean, I guess I'll just type it until it becomes, if it's like an inconvenience. Well, actually, this is quite nasty to type because it's got all these subscripts in it. So yeah, maybe it would be nicer to just see your screen.
Okay, let me see. How do I do this in Discord mobile? Wait. Could be. Okay. I'm a bit of a technological. Am I sharing my screen?
Mm-hmm.
Is it sharing or?
Mm-hmm. Yeah, I can see it.
Okay, nice. Then quickly not box myself.
Oh, it's the same thing.
Okay, this
Yeah.
was for the next problem.
It's 6:10 over
So
there?
you can see
Wow.
my. Sorry? Yeah,
It's
6:10.
6 o'clock.
Yeah. So problem 2, right? It was like we have this sequence A n plus 2. Is it big enough? I don't know.
Yeah, I can see it.
This is,
I'm zoomed in.
Okay. A n plus 1 plus n. Just this automatic thing where like straight lines, it kind of autocorrects them, but it's really annoying.
Yeah.
Okay. So this is this definition, and yeah, I don't know. Maybe someone in chat has like a super nice strategy or something. But so there's a nice, a really nice trick, I think,
Mm-hmm.
which is based on doing this thing. For example, 2an plus 2 plus an plus 1. We just consider this quantity. It comes a bit out of nowhere, but we can rewrite this using the definition that we're given for this sequence to just 2an plus 1 plus an. So all I did here was just I rewrote this an plus 2 as this something plus 2. I canceled out the 2s, and you're left with 2 copies of an plus 1 and 1 copy of an.
Oh, yeah, I guess I see that.
Yeah, it is a bit. It's a bit out of nowhere. That's the hard part. Yeah, that's the hard part. But this is now that we have this, I'm claiming that this is like really nice because we have this like we're kind of propagating this equality downward in some very vague sense, right? We have this because on the left side we have like the same thing as on the right side, just shifted 1 index up. So like because now on this right side I could keep repeating this to say this is 2an plus an minus 1 by the exact same trick.
Wow. Yeah, wait, can you go over the way you got this at first? My intuition is not clicking in. Like
Sorry,
from
what do you mean? Like
from the first line step to the 2 times a to the n plus 2, like how does the algebra work out there?
Yeah. Let me just write it down in screen. So I'm just to like that, and all I'm gonna do is fill in the definition of an plus 2 like this.
Oh.
You see, right? The 2's are gonna cancel out, and what I'm left
Yeah.
with is an plus an and an plus 1.
Yeah.
So we can just simplify it like this. And that's really, really nice.
Yeah.
So
Yeah.
I mean,
wow.
and then you can keep repeating this trick. Yeah, I mean, this is really nice. This part I definitely didn't come up with, like this part I found. But then the point is, you can keep repeating this until you land at like 2a2 plus a1. Right? You can keep propagating downwards until you're at the very end.
Sure. Yeah.
I mean, technically, right? If you're like really careful, you should prove this by induction or something, like starting from the bottom case and actually like working yourself upwards to the general case. But
Right.
I mean, I think for now it's fine.
Yeah.
But you have this, and like let's give this thing a name, C. So I don't have to keep writing it.
Okay.
Because now if we look at a theorem statement, or what do we want to prove? We want to prove that AN converges to exactly this C over 3.
Yeah.
So now we can. So now that we're equipped with this like really nice thing, I'm saying this is gonna be like quite a, well, let's say, more straightforward exercise. Because now we want to. I'm not gonna write out the full definition, but we want to do like something like this: AN, like the distance from AN to C over 3. We want to bound this by some epsilon.
Sure.
That's what we.
Right.
And
The
I'm-
definition of convergence. Yeah.
Exactly. For some small n bigger than some capital N, depending on epsilon. Blah
Yeah.
blah blah blah.
Yeah.
But now and I guess we can actually worry about like the small cases. Let's say that n is at least 3 for us, which we can always do in the end, right? Like we're gonna pick our capital N,
Yeah.
probably
you could just
quite
say
large,
it's 2.
and then the small
Yeah.
n will be larger. So as long as we pick our capital N big enough in the end, we can like make this assumption that n should be at least 3. And that's also what the previous guy, right, was kind of saying, like, you don't need to worry about what happens in the small cases, like only as you go in the limit. Like more formally, this translates to you can always pick your capital N even bigger, and to exclude like all the like the small cases where it goes wrong, whatever.
Yeah. Yeah.
So now I can rewrite AN again, put it here with the definition of the sequence, namely AN minus 1 plus AN minus 2
Over 2. Yeah.
over 2 minus 3.
Yeah. Okay.
Wait, let me see. Okay, what did I want to do?
And we're trying to come up with a value for n.
Yeah, I mean, I'm trying to. I was trying to reduce this thing. In the end, I think it was something I got, like something related to like a minus 1 minus c over 3, and then the whole thing like by a half. So it was kind of like saying like every step you increase in the sequence, like your distance to the limiting value will halve. So you're getting closer and closer really, really fast.
Yeah. Okay.
Yeah. Okay. Yeah. Okay. I see it now. I was a bit stupid because we have this thing, and now we're gonna use what we just did about this, how we can write 2an plus 2 plus an plus 1 equal to this value c. Because now,
Yeah.
I mean, the whole thing is just gonna be shifted if you index this down. Okay, yeah. Sorry, I'm a bit out of it. I wrote it down and then I deleted it, so I have to kind of come up with it on the spot again. But let me redo that last step. My bad.
No,
'Cause-
I'm more clueless than you
Let
are.
me first on the right. On the right, like we had this 2an plus 2 expression
Sure.
equals to c, and I'm just gonna do some algebra where I'm just gonna do c minus an plus 1 all over 2 equal to an plus 2. This,
Oh, okay. Yeah, I guess so.
right? I'm just rewriting it, and then, I mean, this is a bit of abuse of notation, but let me say this is kind of if and only if, or this is just the same as saying a get an minus 1 over 2 equals an. I'm like, because this holds for every n, so I can just shift the indices down by 2 and it's still fine.
Yeah. Yeah. Okay.
Right?
Sure. Yeah.
Yeah, it's a bit arbitrary looking, but this is what actually will help us.
That is kind of weird. Yeah.
Yeah, it is. Because now we have an expression for an purely in terms of an minus 1 and this value c. That's kind of the point. So I can substitute this expression for an that we have on the very right into our thing that we want to.
I see. That is very clever. Yeah.
Yeah, that's the takeaway here, right?
Yeah.
So we're gonna get like c minus an minus 1 over 2 minus c over 3 all in absolute values, and now this can be simplified, right? We get, if we split up the fraction in two parts, we have a c over 2 and a minus an minus 1 all over 2. So if we combine the two things with c in the numerator, I always forget in English, like the top part of the fraction, that one. We just get a c over 6, right? C over 2 minus c over 3 is c over 6. And then we're still left with an minus 1 over 2.
We can just separate that. Yeah. Okay.
Exactly. And now I'm gonna put the 1/2 out, and I get c minus c over 3, of course. C over 3 minus an minus 1.
Okay.
So now if we look at like the very left-hand side, and I mean, let me write it down as an excess graph. I can just, because we're doing an absolute value, it doesn't really matter. Like I can take the minus of whatever is in the absolute value.
Right. Yeah.
So that's fine. So on the very left-hand side, we have kind of like the difference from the nth term in the sequence to the limiting value. And then on the right hand, we have that it's half the difference of the previous term in the sequence to the limiting value.
Yeah. That's very clever.
I guess. Yeah, I mean, yeah, it's very nice. But so now you can kind of, I guess, intuitively see why this should converge, right? It's like in every step of the sequence, we're getting closer and closer to the limiting value by a factor of 1/2.
Right.
By a factor of 2, I'd say.
I forgot what we were actually trying to show with this question.
Yeah, actually, it's that this sequence an, I had to put it at the top here, that it converges to c over 3. C was just this name I gave to this one expression.
Oh, gotcha. Yeah. That it converges to that.
So,
yeah.
Exactly. So that's why we have this minus c over 3 also within these absolute value, right? That's our like limiting value that we want to show where it converges.
Right.
So now you can, I mean, I haven't written the rest out, but I think, I mean, do you want to go through the rest of the exercise, or do you think that maybe if like having this equality or this relation, do you think you could come up with maybe a way to complete it, kind of?
I'm not exactly sure how you would go to showing convergence from here, though.
Yeah, fair enough. I can
Yeah.
I can throw like a little bit more. From this is all I wrote down, and then I said, oh, I probably can show it from here. So now we're gonna see if I can back my claims up.
All right. Yeah.
So let me let me write it down this thing again here, just so we have. So we're trying to show an goes to C over 3, and what we know is that an minus C over 3 in absolute value is just half of like 1/10.
Yeah.
So
Just
and this
half
we
the
know
time.
like these for all n words makes sense, right? So I guess n should be at least 2.
Yeah.
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 And I guess you can now, I'll just write it down. You can technically you should use induction again, but you can propagate this inequality or this equality also downwards to get that an minus c over 3 should be some power of a half. Let's think about it. And then the last term, a1 minus c over 3.
Yeah, what power of a half would it be? N
Yeah.
minus...
Yeah, there's some like make sure that we don't get the indexing wrong. So let's just do an example. If I start at n equals 3,
Yeah.
then n equals 2 is 1 power and a half. N equals 1 is another power of a half. So I guess you always get 1 less.
Right.
It makes sense. That makes sense. Okay, it's like from n, I need to take n minus steps downwards to get to 1.
Yeah.
Fair enough. That makes sense. So, and this equality makes sense, I guess, for all n. It also works for n equals 1, right? Because then we just power of a half just vanish.
Yeah.
Like to the power 0, so it's just 1. So it still works. So
Yeah.
this works for all n greater equal to 1. And now, okay, like this is all like just background work. Now we can actually start proving that this thing
Yeah.
converts. It's
Yeah.
pretty terrible. I'm curious to know. Yeah, probably there are other people who have like way other tricks which are like, I don't know, easier or something. I'm curious.
I wonder.
But,
we got Cool Fire from last time. He knows a thing or two.
Nice.
Yeah.
Okay. Oh, let me see. Okay, so we want to again. We're gonna play the same game as last time, right? Where we have we want to bound this thing by epsilon.
Yep.
We want to find. We're gonna work our way backwards. We want to find our capital N.
Yes.
But now I'm actually gonna use this. I'm gonna rewrite this as. Or let me do this a bit more so it works more clearly. I'm going to use our inequality or sorry, equality an minus c over 3. And you know what? Maybe I'm gonna give this a1 minus c over 3 in absolute value another name. I'm gonna define this thing to be b or something because I don't want to keep writing it every time.
Okay. Yeah. Good trick.
It's the best. It's the most worthwhile trick.
Yeah.
And the point is, right, because this, no matter what this a1 might be, this b is always going to be some constant. So what we want to show is that if you choose a small n big enough, that this inequality will hold true no matter the epsilon. I guess I should write down here. Always that epsilon is bigger than 0. Some arbitrary epsilon bigger than 0.
Yeah.
And now this is, I don't know, this to me already feels eerily similar to the previous exercise. So this is what let me write it down again. This is what we want. We don't.
Yeah.
And just rewriting the algebra, this is equivalent to wanting the following. Right? B, I guess I should say that B is a priori bigger or equal to 0.
Yeah.
It could be by chance that B is actually equal to 0. Then like this step I'm doing by dividing by B, of course, is not technically like legit.
Right.
It only is. But like, so let's worry for a second about what happens if B is actually equal to 0. We want this inequality in green to hold. But if B is equal to 0, well, we're good, right? Because we already assumed that 0 is less than epsilon.
Yeah. Yeah. Or epsilon is greater than 0. Yeah. Okay.
Yeah, exactly.
Yeah.
So I'm not going to write it down, but this is like technically something you should worry about. Like, oh, what if B was equal to 0? But this is okay. So then we're fine, right? Then this works out. So now we only have to worry about what happens if B is not equal to 0, that is B is strictly positive. So let me write it down. So then we can actually divide by B. And because B is positive, the sign doesn't flip. So we want to show this inequality. But again, this epsilon over B, I can just give it a new name, right? Like let's say epsilon prime. I don't know.
Yeah,
it's again some number which is positive. And we want to show that if we take this exponential of something, in this case a half, then it will eventually be smaller than this epsilon. But this is exactly what you showed in the previous exercise when talking about the case where x is less than 1.
Right. Yeah, you're right. Yeah. It converges. Yeah.
Yeah, right? It converges. Yeah. So, yeah, or it's like this was like in part of it, like, right? So, showing that this works, so you can either copy paste your proof from here, or you can do the ln thing, like the natural log thing that we did last time, or use this binomial trick again, or just say, I already did this.
Yeah.
But this works out.
Okay. Yeah, that's not terrible at all. Yeah.
No. Yeah. No. Exactly.
Yeah. I guess. Yeah, the general trick to solving these problems is kind of just working backwards once you have an end. But they're just making me do some kind of difficult algebra, I guess, with these sequences.
Yeah, it's a bit, sometimes it can be like that. I mean, this one, I would say, like, at least how I did it, this is not very easy and not easy to come up with at all. The other one, what he said was this binomial trick, it's really, really useful. Or maybe I can write down something, like how it is often used in real analysis. So before we saw, right, that like 0, that's like 1 plus h to the n, right? You can write this as, what was it, like 1 plus nh, and then like these higher binomial, something h squared plus higher order term. And then you can estimate this by 1 plus nh. Or how you will also often, how you often see it, it's called, I think, Bernoulli's inequality.
Bernoulli's inequality.
Useful name. It's quite a, quite a famous one, and because it's very useful in in real analysis, and it's, I guess, more or less saying exactly that. That just this inequality here holds. It's just not mentioned this binomial step, and this binomial step is like one way to do it. It's also like a kind of, I don't know, I want to say standard, but a common exercise to show that this holds just with induction. So before you have the binomial theorem. Because the other guy mentioned like, the binomial theorem is easy, blah blah blah. Defining the natural log is hard, and he's completely right. But on the other hand, I don't know. Sometimes, or at least if I think back in my courses or my real analysis course, I don't think we were allowed to just whip out the binomial theorem in general and just say these things. We have to, I think, prove this inequality by induction, like without reference to the binomial theorem, and then use it.
Yeah,
but
that's
this,
cool.
exactly. This inequality, it's really useful because, right? I mean, you're kind of already starting to see, right? In real analysis, it's all about like estimating and doing inequalities and like simplifying your expression by doing some estimate to make it simpler. And this is like one of those like really useful ones because you have some exponential thing, which is generally harder to work with, and you can just estimate it by something linear, which is way easier to manipulate in general, like in conjunction with other things.
Yeah. Yeah. That does make sense. Yeah.
Yeah. I mean, are you happy with this working out of this exercise?
I am. Yeah. I think what I'll likely do is just on my own go through and try to formalize all of these things.
Fair enough. What I can do is send you like the PDF of these notes after some later on Discord or something, so you can look at it again. Because
that would be nice. Yeah. Yeah. Are you familiar with it's funny, this book the other guy told me, I don't know, his Discord name is Fat Ugly Poor, but other than that I don't know what his name is, but this book seems very intuitive.
What I didn't follow. Can you tell me like what's the name of the book?
I can send you the URL actually.
Okay.
Oh, my Discord is way zoomed out. What is going on with this? Yeah, understanding analysis.
I feel like, because there's like I've heard of like a really famous one, which is like, I think, Stephen Abbott. I think I haven't read it myself, so like I can't give you like actual useful feedback or information, but I've heard a lot of people talk about this very positively.
Yeah.
That's what I can say. It's like a very famous one, like doing analysis like intuitively and stuff.
Have you found do you ever use a textbook that your class like didn't recommend? Like
sometimes. I have to say not too often. In general, we don't really, or I haven't used textbooks even that often. It sounds kind of weird, but it's like they often use like, or at least in undergraduate, they often use like self-written lecture notes, where I think I told you this, but it's like you're the lecturer, or people give the same course every year, so they write like lecture notes like exactly for that course, where it's exactly, they cover the same thing every year. So you only do what's in those lecture notes and exactly that, which is really useful. But so we haven't had that many textbooks, but I don't know, for me they also, I feel like in some courses I have, but this was always based on like, was the textbook it or not? I don't know.
Right.
It can happen.
Yeah.
But in general, I would encourage it. Like, if you want to and you find like some other book, like for example Abbott, I would definitely also use it, and not only your usual one.
Yeah. Yeah.
Because it's actually like something like real analysis, right? It's so like, I don't know, standard, like so widespread, like so many courses will cover more or less the same thing, especially at the beginning.
Yeah.
So it's perfectly fine to use like another book. Yeah.
Right. That makes sense. Yeah. Yeah. I wonder like how, I mean, you're expected to solve these, I guess, without a ton of like external help, but like I would have never thought to invoke Bernoulli's inequality. Like that's the first time I saw this today.
Yeah. I guess, I mean, if you've never seen it before, you wouldn't dream of it. I agree.
Yeah.
But yeah, it's really one of those you have to have that one in the back of your pocket or something. I don't know. I don't know. Some of these, because if this, as you said, right, these are kind of like the first problems you're really doing like with properly proving convergence.
Yeah.
Like I wouldn't say these are the easiest ones or the ones like that I would expect like for a first time, to be honest. Like the very first one,
Yeah.
I think if you use the log like we did last time, it's kind of okay. But like, for example, now this second one, I think this is not so easy, and it's not really about learning what convergence is, right? We have to come up with some algebra trick. This was like the main part of the exercise, and then actually showing convergence was like a bit whatever.
Yeah.
Like you didn't get to practice with actual showing convergence so much. So I don't know. I don't know what to think of these exercises.
Yeah. You do make a good point. I wonder, just from my own understanding, if we could do like a question like not out of the homework, but like based on convergence, you know, because it looks like, yeah, I don't know. I'm still trying to get the intuition of. Oh, he said it was.
Yeah, I think that's a very good idea.
Yeah.
I can see if.
Do you have any problems you
find,
like in terms of?
What do you mean exactly? Like types of problems, or?
Yeah, I mean, you know, any like really problems that like really get to the heart of the definition of convergence?
Off the top of my head, I'm afraid it has been a while. I'm looking through Abbott at the same time, like the first chapter. You probably have some.
Yeah, the definition of convergence is around page 42, I think.
Yeah.
So I'm guessing there'll be exercises.
With that theory, talking about the algebraic integers then. Wait, I'm in the wrong chapter.
Page 47.
Page. Yes, the limit of a sequence. But 47. There are the exercises. Okay. What happens if we reverse the order of the quantifiers on definition? I think this first one sounds funny. It sounds quite interesting.
What happens if we reverse? A sequence of Verkanges? What?
So yeah, it's just like, it's kind of like testing you, right? What if we had the quantifiers in some other way? Like what semantic difference would there be? Like with this new notion, which we call Verkanges. I think this kind of helps you or will test you to really like understand what's going on with this convergence.
Okay, a sequence of Verkanges. if to x, if there exists an epsilon greater than 0, such that for all n in natural numbers, it is true that n is greater than or equal to and implies x sub n minus x is less than.
Yeah. So the only thing that's switched here is that you switch the for all and the there exists with the in front of the epsilon and in front of the capital N.
Right.
Like the intent to use that.
And what does that do exactly? There exists. That's quite weird.
Yeah. So it means there exists a number that for all possible choices. Okay, I think this is kind of funny. This would be interesting. I mean, you can just go through it like he what he says afterwards in the exercise. So first give an example, then it's like a counter example, blah blah blah. So can you come up with an example of a verb conjugate sequence? I would say just try out some like really easy sequences where you can like easily test if this definition works or not.
Or like n, for instance.
Exactly, that's the best sequence. After maybe like a constant one, yeah.
Right.
So,
Well, I guess
like
n would diverge, so trying a constant one is, well.
We can try both. See what happens.
Say if it's 1, then there exists an epsilon such that for all n, that n greater than big N.
You can maybe you can try to sketch again like this kind of graph or diagram that the previous guy did, right? Where like in terms of these error margins and this epsilon, some error bar. Try to see like in that kind of way.
Yeah, I don't have a good way to show this paper, but.
Fair enough. Yeah, okay, that's it.
Yeah. So, proving theorems about. Okay, so if there exists, if we've got an epsilon greater than 0 such that for all n, it is true that there's an n greater. It's weird to have a for all and then to have something greater than that. It's like that n gets arbitrarily big.
Exactly. It comes to a very key point. This is weird. So maybe you can. I mean, you're already kind of going ahead just for this, but yeah. So what does this tell you? Like that you have this for all, and then you're also saying something about for all and bigger than that.
Yeah, it's a weird double for all. And you're saying that that's less than a constant epsilon. That doesn't really seem possible in any case.
Well, yeah. I mean, I feel like if you understand what this double for all does, that's the weird part. Then it will become.
Okay.
You'll see that actually, I think will be possible. Yeah. But if you try to like, I don't know how to phrase this because I'm not a programmer. As you have noticed, I'm a mathematician, so maybe I'm saying weird things. But if you try to kind of think in some abstract way about a for all as like a for loop that is testing some condition, right? You have for all and then some statement. So kind of, I mean, you have infinitely many things, so it's not really a loop, but it like, you know what I mean? Like, it goes through each possible value of capital M, and then we have to check if it's decide whether the statement or not, whether the statement is true or not. So let's say Also, yeah, I don't know what what Abbott's conventions are. If he says that the natural numbers start at 0 or 1. But in the end, it doesn't really matter. But let's say it starts at like capital N is equal to 1.
Yeah.
And then we have this statement inside. So we have for all small n,
Yeah.
bigger or equal to 1, we have that some implication is true. Okay, interesting.
Okay.
What happens if capital N is equal to 2? Then we have that for all small n, bigger or equal to 2, that same thing on the right is true.
Yes.
So we're kind of double checking this condition. You know what I mean? This was already contained in the capital N equals 1 step.
Right. That is really weird. Yeah.
Indeed. I mean, it's not wrong. It's just indeed weird.
Yeah.
So, and so then if you go so what happens if you do N equals 3, for example, capital N equals 3?
Then you're checking for all lowercase n greater than or equal to 3, which is, again, just a kind of a subset of what you checked before.
Exactly. So, you keep checking the smaller and smaller steps. I mean, it goes on forever, but we're mathematicians, we're not programmers, we're not worried about this.
Yeah.
So, the only thing we need to worry about is the capital N equals 1 case.
Right. Yeah.
So that's kind of right? It kind of gets rid of 1 for all quantifier, semantically.
Right.
All we really need to worry about is if there exists an epsilon greater than 0, such that for all small n bigger or equal to 1, this implication is true.
Yes. Okay. And we can just pick an arbitrary epsilon.
Yeah. Well, we have to find anyone. Anyone will do. So what is this? What does it mean that there exists some epsilon such that every possible value of the sequence stays within an epsilon bound of the limiting, limiting value is not really the right term because we're having a new concept.
Yeah, what does that mean exactly? I mean...
I can try, maybe I can sketch again. I can share my screen.
Yeah, sure.
Cool. Okay.
After this, someone suggested an interesting idea, Alexander, which is practicing the mechanics of something for an intuitively known convergence 1 over n.
That's a really nice one. That's a good idea to ask afterwards.
Yeah.
Yeah. So let's see. We have but you can see my screen, right?
Yep.
We have some axis. Let's say we have some n, right? And we have some sequence, right? We have 1, 2, I don't know. Yeah, this won't be as pretty as the other guys. I'm not very good at drawing. But let's say this is x1, x2. That's right. X1, x2, and I don't know. The sequence does something. I'm just making stuff up. And we're given also some real number x. Let's think about the horizontal line corresponding to the height of x. What we have to show is that at each step, we have to find some epsilon, some error margin, such that at each step, let's say epsilon is this.
Yeah.
The sequence value is only epsilon far away from the horizontal line. So for example here, this epsilon wouldn't work because x equals 2 is outside. but for example here it would work. You know what I'm trying to sketch?
Yes, yeah, I see what you're saying. Yeah, yeah.
Yeah. So like for example, this epsilon wouldn't satisfy, but let's say the sequence would be doing this, like I have here, and then it would stay constant forever. It would stay exactly on the line forever.
Yeah.
This is a possible sequence, and then we take some other value for epsilon. Let's say I take epsilon like something really big, like this interval.
Sure.
And you can see that if we believe that when the sequence will be constant on the right, we see that at every possible step, the value of the sequence is only epsilon far away from the horizontal line, from the x. So this sequence would satisfy the condition, as in this sequence is very conjugate to x, because we have found some epsilon where this works.
Mm-hmm.
But note, for example, the epsilon is not like unique at all. Like I could have made the epsilon much bigger, and everything would have still laid within the epsilon boundary.
I see. Yeah. So as opposed to converges, this is like you're choosing an epsilon that contains everything, or that all parts of the sequence this holds true for.
Exactly. You're choosing one epsilon where it has to contain everything. And then we say it's very conjugate to x, if that works. So for example, if I do a constant sequence, right, this would also work, because I can choose like any epsilon would work in this case, because they're already, all the values are on that line.
I see. Yeah.
But what about we do the identity sequence, like you said, where an is just equal to n, like this, and so on.
Yes.
Does there exist such an epsilon where this will work?
Not exactly, because you would always have to choose some bigger.
Exactly.
Vercongement.
Yeah. Exactly. So this one doesn't verconge, as they say. But so what this comes down to, I just tell you, but it turns out that this is equivalent to saying that the sequence is bounded.
Huh.
You kind of imagine like why this should be the case.
I guess that kind of makes sense. There'll always be there's like a value greater than everything.
Exactly. And it's a bit slightly different than how you would normally see like being bounded defined.
Yeah.
So this definition is dependent on this parameter x, right? We're talking about verconging to x.
Yeah.
So this is kind of weird. So you're saying that the sequence verconges to x if and only if it is bounded, which is a notion which doesn't depend on this x. So it verconges to one number x exactly if it verconges to all real numbers.
Right.
Which is really weird.
That is weird. Yeah.
But so this is what this exercise is kind of doing. But it's a bit of brain gymnastics. It's not a useful definition of being bounded, I think. It's just like getting used to these quantifiers.
Right. Yeah. I guess that does help a bit for sure, but I think solving convergence of like 1 over x. Yeah.
Yeah, I think that's a very nice one. Do you think you can like set it up so that you can write on your own, show it on screen?
Yeah. Likely be. Oops. Alright, I'm just gonna create like a new...
Yeah, I'll be gone for like 2 minutes. Okay, I'll be right back.
Okay, cool. How's everyone doing? I can't really read chat when I'm on call with someone, but I also can't tell how many people are watching. It might be 3 for all I know, but something clear like, yeah. And then 2.2.3. Convergence of a sequence. Man, there's like an infinite amount of math to know and read. Jeez. Just goes on and on. Oh, welcome from Saudi Arabia. Alright, showing convergence of... So let me see if I can get started on this. Of 1 over n. Okay.
Are you gonna do it on Typst?
Yeah. It's too hard to get paper working.
Fair enough.
Okay, so let me try to just think of the definition just to strengthen it. So we're yeah.
Or before you try to get like the formal definition, do you have already like a vague intuitive picture of what the definition should say, and then kind of extrapolate from there?
Yeah, we want to show that the absolute value of like the nth term minus what it's going to converge to, which is 0, is less than an epsilon.
Yeah.
So, I mean, like we don't use pipes actually. Like a, which is 1 over n, and then minus, and a is less than. And then we're looking for a value of big N that all little n will make this inequality true. And this is just, you can say 0.
Yeah, exactly.
Okay.
Yeah. So I mean the stream is a few seconds behind, but from what you're saying, that sounds like you got it exactly right.
Yeah. Okay. And then to actually get this, we could do some rearranging. Like, we're looking for a value of big N.
Exactly. Yeah. So the strategy always, I think, especially with these proofs, like the working backwards strategy is like the go-to. It's always, yeah, very, very useful.
Yeah. And we can define this in terms of epsilon. So like solving for, what you want to do is solve for this little n.
Exactly.
Okay. which we could
Because that
do.
would give us some inequality, right, regarding n. Like we want some lower bound for our little n, and we can choose our big N to be like, let's say, slightly above this lower bound, whatever it is.
Right. I see. And we can safely multiply by n out of here because we know n is positive. I mean, I guess we don't
Exactly.
necessarily, but
I mean, we do, right? N is I mean, it's whatever. It's at least, or if this is their definition of a sequence, N should be at least 1. So it definitely is positive. Sorry.
right.
And
we
yeah,
can
and we don't have to worry
say-
about the absolute values in this case.
So we can say our big N is equal to 1 over epsilon.
Yeah, I mean, right, to be like very nitpicky, but it should be, right, big N should be at least 1 over epsilon. So this small n will be bigger than that, but probably in your definition of convergence, they said that this capital N should be an integer. So you should round it you should round it up, like you should use the ceiling function of this 1 over epsilon to actually like get one specific capital N. But indeed, like any big N, which is at least 1 over epsilon, works, but very, very technically you should pick it to be an integer. Or an epsilon
Gotcha.
function.
Yeah. Because n is, yeah. And then any n greater than that, and that's all we have to do is show that that n exists as 1 over epsilon.
Exactly. But maybe this is a nice one to actually try to write it down carefully. How would you write the proof down?
Yeah, that's a good
The
point.
full proof.
Yeah.
So from like the very, very start. I mean, let's say you're given this sequence, right?
Right. Yes. And we don't okay. And I guess you could say like
What's the very, very first thing you want in your proof?
I'm not sure, I guess.
If we think about the formal statement again, right? Because we're trying to, what we're now actually doing when we're writing it down, we're trying to prove this formal statement. Like,
Yeah.
what kind of quantifiers are in there? It starts with like, for all
I see.
epsilon, there exists an n.
Yeah. Yes. Yeah. I guess.
So we should kind of, when we're trying to prove it, like we have to prove it for an arbitrary epsilon, right? We have to show something. So we should say that in our proof, like let epsilon greater than 0 be given or be arbitrary or whatever.
Okay. And do I... Oh, never mind. Be given or be arbitrary?
Yeah, whatever you feel like. Also just let epsilon greater than 0, but I think that's a bit short. It's whatever, just to signify that you pick some arbitrary epsilon greater than 0 and you fix it from here on.
Yeah, I guess I've also heard fix. Like that, I don't know.
Yeah, it's all good.
Yeah. And we want to show that for all, or we want to show that there exists an
Yeah,
n,
exactly.
or exists a capital N, where for all n greater than n, we have, let's see, whenever n minus 0, and these are
Yeah, exactly.
okay, yeah. And then just based on that scratch work, we can say choose n.
Exactly. Now you pick your n at kind of the beginning of the proof, because now we're going back and forth.
Choose 1 to be, or n to be 1 over epsilon squared, and then
1
if
squared.
or 1 over epsilon.
Yeah, yeah. Or the
Yeah.
ceiling, or whatever you want. Yeah.
Oh, right. The ceiling, just to be rigorous.
Exactly. Yeah. I don't know if they would deduct points for you for homework. I guess I can imagine some people would, like in the beginning analysis course, that they really want you to really be good with the definitions and follow them to a T.
Yeah, that seems reasonable. And once we choose this, do we show that by using that as a value of n, like?
Well, not exactly that one, but we have to show it for every n. What was it, bigger or equal to capital N? So again, we're proving now, we're kind of unwrapping the formal definition. We had a for all epsilon, that there exists n, and now we have a for all statement again. So we again have to choose an arbitrary small n, bigger or equal to n, to prove the for all statement.
Yeah. Okay. Equals, which is the same thing as the ceiling of 1 over. And then if we want to show that the absolute value of 1 over n is less than epsilon, but if we have let's see, what's the best way to go about this? Just plugging it into
I mean, yeah, now you kind of, or how these proofs then go is now you write down your scratch work backwards, kind of, to get, because the scratch work started like where you need it to end up. Now when you actually write it down, you use your inequality, namely that your small n is, well, it's bigger or equal to capital N, and therefore strictly bigger than 1 over epsilon.
Yep.
I guess there's one, again, some super nitpicky point. I guess we should technically pick our n as what we have it now, but plus 1. Because otherwise you will only get a non-strict inequality in the end, but we want a strict inequality.
Right, okay. So, I guess I can get rid of that and say this. And then Well, oh, I see. Then we get rid of this non-strict. You can just say that.
I don't know. For me today, this stream is like quite long behind. I don't know. Pretty much long. But yeah, exactly. So, well, at this point, you still have the non-strict one. If you choose your n to be, I guess what you should do is you choose your big N to be equal to ceiling 1 over epsilon and then plus 1. So that if you say that your small n is less than or equal to big N, you can then conclude that small n has to be strictly bigger than ceiling 1 over epsilon and therefore also strictly bigger than 1 over epsilon, because that's what you want in the end.
Right.
It's a bit confusing to you know what I mean?
Yes. I think so. So if we have little n greater than or equal to big N, is it greater than or equal to the
this one bigger or equal to indeed?
Yes.
So this is our assumption, like, so we suppose we have some n than this.
Yeah.
Then we can now say that because of the way we have defined it, for example, our big N is strictly bigger than 1 over epsilon. And then we conclude that small n is also strictly bigger than 1 over epsilon.
Oh, I see. Choose n to be.
Exactly. Because if we didn't have the plus 1, then it could happen that a capital N was accidentally equal to ceiling like 1 over epsilon. So we just have this plus 1 to make sure that we're at this strict limit.
Yeah. Okay. All right, and then we have that n, and we want to show that kind of reversing the scratch work.
So the first thing to conclude is from the inequalities that we have, that you want n, small n, to be strictly bigger than 1 over epsilon.
Right. Which we actually have based on that choice of big N.
Exactly.
Well, we have that. Sorry, this is probably what you were saying before, but we have that it's strictly greater than that plus 1, correct?
Or the way you've written it down, yeah. But how I had meant it was the way where you had n equal to the plus 1 thing, and then you could conclude that it was strictly bigger than without the plus 1. But either way is fine.
You have little n equal to that?
No, it's big N equal to the plus 1 thing. Right, this was your choice, where you chose that.
Yeah.
Then you can say that this big N is ceiling 1 over epsilon plus 1. Well, that's definitely strictly bigger than just ceiling 1 over epsilon. And that again is bigger than or equal to 1 over epsilon.
I see. So the plus 1 here is redundant.
Wait, I don't know exactly what you mean by here.
Yeah, I guess the stream delay is tough.
What you have, yeah. What you have now is correct. Yeah, this is good. And then you can do one more simplification step where you just note that the ceiling 1 over epsilon is greater than or equal to just 1 over epsilon. And with that, you can now conclude that small n is strictly bigger than 1 over epsilon.
Oh, yeah, we can put Okay. All right. But I'm still confused as to, so this doesn't complete the proof, does it? We need to.
Still setting it up, unfortunately. No, because, or I mean, now you have it up to your scratchwork. Now once we have that small n is strictly bigger than 1 over epsilon, then you can use your scratchwork to conclude that absolute value of 1 over n is less than epsilon.
Right, I see. We can rearrange. Yeah, okay. We can say and then we can just put the abs around that because it's also positive.
Yeah. I think your inequality flips somewhere in between. One of the two. A few steps back.
Oh, yes. Yes, you're right. Oh man, there's a lot of the. This is the problem with typing math.
Yeah, no worries.
Okay.
Exactly. So now, like by the definition, you're kind of done. Because what we have shown, we have like unpacked all the quantifiers, right? We had the for all quantifier we set up by letting epsilon be arbitrary.
Yeah.
We set up the there exists capital N by choosing n, and then we set up the for all again by using the letting small n be arbitrary, and then we just had some statements which we have proven, like this inequality. Wait, no, your inequalities were right. I think I'm retarded. Yeah, no, here, sorry, yeah, my bad. Okay, no one in chat caught it though, so I'm safe. They can't say anything. Damn. Right, because yeah, I don't know what I was thinking. You want the whole thing to be smaller than epsilon.
Yeah.
Nice. Exactly. So, yeah, this is, I mean, it's a very short proof, right? It's
yes.
All in all.
Yeah. Okay.
Like this, yeah, for this.
The unpacking of the quantifiers was very helpful to understanding how to do this, actually. That seems like, yeah, a big step.
Exactly. And yeah, for these convergence proofs, it's always like the same recipe as this, where like the beginning of the proof will always be the same. You say 6 epsilon greater than 0, like out of your magic intuition, which you did in your scratchwork, you choose some crazy capital N. You say let n bigger or equal to n. You do your scratchwork backwards, and you arrive at what you want. It's like it's always the exact same thing.
Yeah. Yeah, algebra just differs on different times. Yeah.
Exactly. And then in these algebra is sometimes where you have to do like clever estimates with like Bernoulli's inequality or whatever, the triangle inequality, the most useful one of them all.
Yeah, I see. Yeah. Someone DM'd me. I think there'd be an additional clause that is epsilon goes to 0. There will exist an capital N such that for all lowercase n greater than capital N, epsilon less than 1 over n. I guess I can. Oh. Let me throw this.
I don't know. Also, some people in chat are being like hyper pedantic. Which fair enough.
You technically
They're
need
saying
Archimedean principle to find ceiling whenever.
They're technically right. As in, if you don't want to avoid using the ceiling principle, because we just needed some capital N, which was strictly bigger than this 1 over epsilon, and there is something called the Archimedean principle for the real numbers, which just said that for every real number, there exists a natural number larger than that.
Gotcha. Okay.
Yeah. Which is like something very obvious, but yeah, technically.
Yeah. But this is definable. This is doable without ceilings.
Yeah, I mean, we could. Yeah, it's just like, it's a bit whatever. You just have to make sure to define some natural number, which is strictly bigger than your 1 over epsilon. Exactly how you do that? We kind of did it by like fixing one particular one. We were saying, this exists.
Yeah.
And the other one is kind of just there exists some by the Archimedean principle. Let us choose one of them and not specify further. Which is non-constructive, by the way. Non-intuitionist mathematics. So big fat L, I would say. But no, it's fine.
Great. Good luck with your math exam. Barbecue. Yeah. All right. This book also really seems like much more solid than the one I have. This definition makes more sense to me.
Yeah. Which is this other book that you have? I saw the Apostle one yesterday.
It is. They're both Apostle. It's weird because for some reason the title page is in Mandarin, but
that's always great. Yeah.
The rest of it's not. I'm scrolling on it. It's not much as. There we go.
Second edition. But like, is it really like a different book, or is it just different versions? I don't know.
Yeah, it's. Yeah. Yeah.
I just see the book Mathematical Analysis, which is what I think you have. I don't know.
Actually.
Well, it doesn't really matter. But yeah, no, I've heard very good things about Abbott, like the other book.
Yeah. Yeah. All right, cool.
The textbook is at a very time in its life. Yes, very much.
Yeah. Let's see. Do you have time to do like one more?
Yeah. Do you want to do like convergence proof thing?
Yeah, I think that would be good. I think because that convergence one was very helpful.
That's nice. Or do you want? You can also, I don't know, whatever you prefer. You can do like a similar one with convergence, or you could do maybe one where it's like an easy one to see where diverges.
Yeah, that would be interesting actually. Just like does n diverge?
Exactly, just an equals to n. Can you show that diverge?
Right.
and I guess we'll use, because he, the previous guy, what he did with divergence was certainly correct. But he kind of did it right, or he also said something about, I think this is not maybe the definition that you would always see, but what he showed is that the sequence is unbounded, right? It eventually gets bigger and bigger and bigger, which very much implies that it diverges. But I think it's also good to, or if you want to practice like with the actual definition of divergence, which is just, right, the negation of convergence.
Right, and the negation of converges would be, it's kind of like a
Yeah, you can.
yeah, I guess I'll try writing it out. So like there exists a big N. Is that the outermost?
Well, first let's first write it down, the definition of convergence,
Right.
and then we can
Yes, such that for all n greater than or equal to that n, we have a sub n minus a. And I guess actually we have a we're technically omitting here. There could also be like a for all.
Yeah, if I were you, I would write down like everything. This will help you with translating the process. Like if you leave nothing implicit, it will be easier to negate the whole thing.
Right. So this
So this is your definition for convergence. I think I would slightly alter it.
yeah.
As in, it's perfectly fine, but maybe for the negating it, like if you look at the second most inner part, as in just from the for small n bigger equal to capital N,
Yeah.
what this is actually kind of saying is that for all small n in the natural number, n bigger or equal to big N implies the inequality. This is kind of, if you want to be real pedantic with like logic, this is shorthand notation for that. And I think
Gotcha.
maybe writing that out like that will kind of help.
Oh yeah. I think you're right. I think I see what you're saying. Yeah. So for all n, and then within here, like that. Yeah.
Exactly. Yeah. And then to be, I think again for the translating thing, we can be even more pedantic in saying like, what does this like semantically really mean? It doesn't just say the sequence converges. It says ever so slightly more, as in the sequence converges to the specific real number A. It's like slightly more information.
Okay. Yeah.
Because why is this interesting in our case? Because when we want to say that the sequence diverges, this is saying that it does not converge for all possible values of A. Like it does not converge to A for all real numbers of A.
Right. So should there be a quantifier on the A?
In the convergence case, no. It's just what this definition, or well, you can do it. If you just want to say the sequence converges,
Yeah.
you can add a there exists A at the very beginning.
Right.
As in there exists some real number and the sequence converges to that number.
Yeah. And oh, I see. I guess for the purposes of just as an exercise of negating this,
Yeah, because now this will, yeah, this is very good, because this will, if you do it with this quantifier, then it's easier to negate, because you want to technically negate that statement where you have the quantifier. You want to negate the statement there exists some number a where the sequence converges to.
Right.
Because if you would do it without the... Exactly. That there exists no such number. That's what you want to show. If you only have it an converges to a, if you negate that statement, well, it just says, and if you prove that, then you've just proven that the sequence does not converge to the specific number a. But that's not what you want to show. You want to show that there's no such possible a.
Yes. Okay, so to negate this, we would get, how do you do exist dot not? Man, I love this language. So such that, and this becomes an exists, an epsilon, and the greater than 0 stays the same. So that for all n, there exists an n. And then negating the implication, there's some trick to this that I don't want to mess up exactly.
Yeah. So when you want to show, like, when an implication is false, aka negating the implication, is when the technical term is the antecedent is true and the consequence is false. Just the thing in front of the arrow is true and the thing after the arrow is false. So if the negation is false, this has to happen, meaning that if you have, like, P implies Q, the negation of P implies Q is not Q and P. It's a bit hard to explain.
This. Not P and Q.
Not Q and P, but the not Q, like the not scopes only over the Q.
And that is interesting. So the and doesn't necessarily matter.
But it does. It's
the order, I guess. Not the.
Yeah, you could say P and not Q. That also works.
Yeah. So we're gonna get the opposite here. And then the and, something like that.
Second. There exists, so there exists an epsilon such that for all n exists an n. Yes, this inner part looks very good. I think you then want a for all as your very, very first quantifier. Because you've kind of, what you've done with this algorithm of doing the negation, you've pushed the negation inward. So I don't know how to explain this in words, but this very first quantifier in front of the a should be in for all.
Oh yeah, yes. Oh, that makes a lot of sense. Yeah, it diverges for all specific values. Yeah.
Exactly.
Yeah.
Yeah, it's just, you kind of have to have in the back of your head that divergence is just like a shorthand for not converging for all possible values.
Yeah. Yes. Okay. Not A and not B. I'm kind of interested by the A implies B negated is A and not B. I believe that in terms of truth values, but is there like another way to like keep the implication in there? You know what I mean? Like Because we're going
I
from
mean,
an and to a yeah.
I know what you mean. I think it will look very ugly though. With implication. Yeah. No, I mean, yeah, implication is I don't like it. I mean, it's a bit of an awkward quantifier because it's not symmetric in its argument, right? So it's a bit weird.
Yeah,
Um,
it
I mean,
is.
but
Yeah.
do you like intuitively like get why it should be not Q and P, the negation?
If I think about the truth table, yes, because the first value, the P, yeah, that makes sense, yes. Because it's like three
Yeah.
truth and then a false. Yeah.
I mean, yeah, I think yeah. I mean, I would try, or how I think about it to get come up with this is like exactly you have to know the truth table for implication, and then you have to think about so when is not P implies Q true? It's exactly true if and only if P implies Q is false, and then if you know the truth table, you know that this happens only when the P is true and the Q is false. So you have
Yes.
this when should our thing be true, and then I think the translating this natural language back into logic, this statement of not Q and P is, I guess, a very natural translation.
Right. Yeah. Okay. So if we are to use this now to show that n diverges, it's a
Exactly.
different
So we can,
process.
indeed, we can kind of already try to set up the proof, and as soon as we hit like an algebra step, we can kind of do our scratchwork on the side. So we can, because there is now a very clear structure to the proof. We have to prove some like nested quantifiers, so we can already kind of set up how the proof should look, right? We should pick our A to be arbitrary, and then we should, well, yeah, think of an epsilon, but we can leave that blank for a second and just see like what we need to show.
Yes. So you mean the big A that we're converging to is arbitrary? So just
Exactly, but that we're not converging to in this case.
right. There is nothing. It's yeah.
And I guess we should also choose a sequence.
Yeah, I'm just
So we
saying
actually,
I'm just saying n.
yeah, that's a good one.
Um yeah.
So yeah, so first we have to choose our big A to be arbitrary, and then so you can say something like let A be bigger than 0, or just sorry, habit of saying bigger than 0, but just let A be given. And then you have to choose an epsilon, but we can kind of leave the epsilon blank for now and just continue with the proof. This is like a trick that you kind of do where you just leave it back and then later you fill in the values you need. Or in the convergence case, you kind of do it with your choice for capital N, where you kind of write down, you fix your epsilon, and then you say, I choose my N equal, and you leave it blank. And then later you see what you need and you just fill it in.
Okay. Yeah. All right. So I'm just trying to understand the opposite structure here for all n. So you're saying we
So now
choose
we
an
have,
arbitrary n.
exactly, we have to choose an arbitrary N because we have to show something for all N.
Right.
So we again need to let the capital N be arbitrary.
Yeah. Okay. And then we want to show that there exists something that satisfies this. There exists an n greater than n.
Exactly, it has to be greater than N, and the inequality has to satisfy it. So now we are given our A, we are given our capital N, and we have the freedom to choose our epsilon such that a certain inequality holds. So now we can do our little scratchwork on the side and seeing like how should we choose our epsilon and our small n.
Right. Yeah, how are we gonna...
Yeah, I think this one, I mean, you can do it in many different ways, but if we again think about the intuitive picture about like this epsilon being an error margin,
Yeah.
and what this specific sequence in our case actually is, we have to show that we always eventually violate the error margin. That's
Right.
kind of what's going on, right?
Yes.
But we have the freedom to choose an error margin. But in our case, our sequence will just happily go off to infinity. Whatever error margin we are going to choose,
Yeah.
the sequence will eventually violate. This is also what we had before, right? We were talking about this bounded sequence and verb conjugate. It was the same. We
Yes.
had an equal to n as an example.
Yeah.
And we saw that whatever epsilon we chose would always just get out of that range eventually.
Yes. This is a little weird
So,
that
yeah.
it's the epsilon is in existence though. I would think like intuitively this would be for any error range this would hold true, but
It will, right? That's just because we are in like a very easy sequence case. There might be other sequences where only some epsilons will work. It's just in our example, any old epsilon will work.
gotcha.
Kind of because
Oh, okay. Yeah.
in the other cases, you like to show it, you just have to find one such epsilon and then you're good. But it just happens in our case that any will work. But again, for the sake of the proof, we should fix some epsilon, and yeah, you can choose like whatever you want. Like for example, like epsilon
I
equals to 1
see.
will work.
Yes. Yeah. Yeah. Okay, sorry. What were you saying about
About what?
about showing that this inequality is always greater than epsilon?
Okay. Exactly. I guess, yeah. Now we have chosen our epsilon. I would just say choose it like to be 1, because then we can, in our inequality, get rid of the epsilon, right? And we can just replace it by 1.
Yeah. Sure. Yeah.
So this is the inequality we want, and we want this for some big enough n. So this n has to be smaller than big N. So we should find like what conditions, and we just have to find some n, right? There exists a small n. So we should, like the proof kind of wants us to provide an example of such a small n. So the easiest thing to do is solve this for small n to get some sort of inequality for small n.
Right, which would just be 1 plus a?
Almost, but we have to be careful about the absolute values here.
Oh, right. I guess we could... Is this a triangle inequality case? Or reverse triangle?
Yeah, wait. I always forget. I think the triangle inequality. Yeah. But wait. We want to have that this is true. Okay. No. Yeah. Reverse inequality. You're right. The reverse triangle inequality, because we want in the end for this to be true. So if we can show something which is smaller than the left-hand side to be less than or equal to 1, then we're good. So we want something smaller, so the reverse triangle inequality will work.
We want something smaller. Sorry, um, I was zoning out because someone in chat said, "Why are we negating the definition of convergence in practice? It's usually easier to derive a contradiction from the assumption that a sequence converges," which is kind of an interesting thought.
Yeah. I mean, it can be, but I think you're at this. Well, apart from the fact that we're kind of doing this to help get used to the definition,
Right.
I think you're at a very at such an early stage where you don't know, in the course, I mean, where you
Yeah.
don't know many other streams from where you could get a contradiction. Do you know what I mean?
Yeah. Yeah, I do. Yeah.
For example, if you already knew that the harmonic sequence diverges or something which you prove much later, then of course you would get a contradiction from something like this, or I don't know,
Right.
whatever.
Yeah. Okay, cool. So is this an inverse or reverse triangle inequality situation to try to isolate n?
Yes, exactly. So yeah, I had to think about it for a second, but the thing is, the inequality we have now is what we want to get to. So we want, if we find something which is smaller or equal to the left-hand side, but still bigger or equal to 1, then we have put something squeeze it in between there, then we would be able to conclude this inequality that we want. So to get something smaller or equal like that, we're going to use the reverse triangle inequality.
Which is something like this.
You can just pull the minus out of the absolute value, or yeah, you know what I mean? Yeah, exactly.
Is that the...
Exactly, that's the reverse one. Yeah, by the way, I don't know if you ever want a interesting or an exercise, the reverse triangle inequality follows almost immediately from the normal one.
Okay, yeah, I'll keep that in mind. All right, yeah. Does the absolute value go... this has it going around the outside of... Does that...
Yeah, it has one more, but the absolute value of something is always bigger or equal to that something inside. So...
Yes.
Yeah. So that statement there is slightly stronger, but it's not that useful in our case.
Yeah. Okay, that is interesting. Yeah.
So by the way, on the right hand side, we just want the greater or equal to, not necessarily a strict inequality.
Oh, on the 1, you mean?
Yes. So this right hand inequality, this is what we want to show. And now, so we want some condition on small n to get this right hand inequality.
I mean, we can rearrange here to get... that.
Exactly.
Okay.
So, I mean, now we're basically almost there. If we think about, again, what do we need to show? What this scratchwork tells us, with keeping in mind that we kind of want the implication arrow to go the other way.
Right.
Given that our absolute value of n is bigger than this 1 plus absolute value of a, then we may conclude that these other inequalities on the left hold, and using those outer inequalities, or that's exactly what we wanted to show based on our choice of epsilon.
Yeah. Yeah.
Oh yeah, that would basically be the proof. Otherwise, if you write down the proof, you should again write your scratchwork the other way.
Right.
I think it might be useful.
Yes, so starting with choose an arbitrary n, and then we have epsilon equals 1. Okay, so and we want to start from the right essentially and work back.
We want to show that this n exists such that we want to show an and statement. If you go back to like the logic thing, we have two things. We want this n to be bigger or equal to capital N and this other inequality. So this sequence, I think it's just because this sequence is kind of easy and funny. We see that the small n doesn't depend on capital N.
Right.
Which
yeah.
is just, I think, happens because it's an easy sequence. So when we have to choose our small n, we should make sure that it really satisfies both the things inside of the and statement. So we should choose it like, for example, the like at least as big as capital N, and we should also choose it to be a natural number, right? So we should choose it to be something like the maximum of capital N and 1 plus, or the ceiling of 1 plus absolute value of A, something. Just to make sure we're really hitting like it being a natural number and making sure we satisfy both inequalities in the end statement.
Right. Okay. Yeah. But even though the ceiling was kind of in contention.
Yeah. Sure.
Yeah.
You can, whatever. You can invoke the Archimedean principle. I mean, the Archimedean principle, it's not useless. It's a reason why there's something interesting. There exists the high level ideas, but there exist things like the p-adic numbers, which are very similar to the real numbers, but you don't have the Archimedean principle.
Right.
But anyway, I'm getting sidetracked.
Yeah. Okay, so working backwards, we can say we have actually after choosing that large n, choose a small n such that n is greater than or equal to, and I guess we're showing we can do something like that.
Choose. Yeah, that works. Well, technically, this you should say you should choose your n bigger or equal to 1 plus A, and such that this thing on the right, because it could happen that your 1 plus A is smaller than big N, and then the sentence technically doesn't make sense, right? You can't choose it to be equal to something smaller than N, but also be bigger or equal to that.
Okay. So like that.
Yeah, but with the inequality in terms of the 1 plus A thing. So N bigger or equal. Say
yes, I see. Yeah. Right. And then we can show kind of working backwards from that work.
Exactly.
Implies that greater than or equal to 1.
Exactly.
And epsilon equals 1. So that's oops. I don't know if I have to say that again, but okay, I see. Yeah, this does.
Yeah, it's fine. You don't need the epsilon equals 1 at the end. I think
It's
it's
clear.
fine. You just
Okay.
do this, and then yeah.
Yeah. Okay. Yeah,
That's it.
that makes sense. Yeah. Yeah.
Yeah, but it's good that you practice these kind of things like this, like really carefully thinking about it, and also like with easy examples, because then if you really get the hang of these ideas, then the rest of real analysis, I mean, it will still be hard, right? But then it becomes more thinking about clever ways to come up with inequalities and stuff, and
Yeah.
this kind of stuff will eventually kind of go automatic.
Right. Yeah. Yeah. It definitely does help a lot to do the practice. Yeah.
Yeah. Do you want to do something else? I don't know. If you've probably been streaming for a very long time, I don't know.
I could do another question if you can. I have pretty good
I can do one more.
Okay.
Do you want to try one of the homework ones, or do you want to come up with like something else again?
Good question. Good question.
I haven't done the next one yet.
Okay, we could look at
I could try.
there are also a lot of good these are, let's see, not examples, but
That's the Abbott book.
yes.
Yeah. Do you think you would like to practice another convergence one or another divergence one?
Probably convergence.
Yeah, that makes sense. Let's
Yeah.
see.
I can feel though, like I can feel the learning seeping in. Like I see the pattern of
nice,
this
right?
problem now.
Yeah, that's nice. I think,
Yeah.
okay, let's come up with a nice convergent one. Let's do something like n divided by n minus 1. Like sequence like that.
N
Two linear
divided by
terms
n
divided
minus
by.
Okay. All right. Yeah,
Something
that's a good idea. N over n minus 1.
Yeah, or n plus 1, right? I mean, you probably, I don't know, you probably learned something like in calculus. Yeah, the American system. I think calculus 1 probably, like if you have the quotient of two polynomials, the limit of to infinity, like if they're of the same degree, the limit to infinity will be the quotient of the leading coefficient. Something like this.
Yes. I mean, wouldn't this would converge to like 1?
Yeah, exactly.
Yeah. Okay.
So it's the easy one because we kind of know what it converges to, right? So once you do these, or when you do these proofs where you have to show convergence, you always, well, not always, but generally you have to know first what is it going to converge to, and then I can actually show it converges to that value.
Right. Okay. So we want to show that for all large n, so I mean, like, choose for all large n there exists. No, am I getting confused at the?
You can look up
Yeah.
again at the different stuff. Maybe you can.
For I guess
So we
for all
want to-
epsilon.
Yes, very good.
I see. Okay. All right. So we want to fix an epsilon greater than 0 because we have that for all epsilon, and then we want to show there exists an arbitrary big N such that n greater than or equal to this n implies that we have minus 1 is less than okay, so
Exactly. So I think this one there's like an algebra trick will make it maybe, I don't know if it will make it too easy, but it will simplify it a lot. Maybe it's nice or very too easy, and then we can change the coefficients in the sequence a bit. So we can see.
Yeah, okay. I guess an algebra trick. I mean, this is kind of similar to the last one in terms of reverse triangle inequality, but
I think you can simplify what's inside the absolute value in this case. Could you do?
I mean, could multiply this by n plus 1 over n plus 1.
Yeah, for example.
Yeah, which would give you a just 1 over n plus 1.
Yes, with a, I guess with a minus, but we're in absolute values. It doesn't really matter.
Yeah. Yep. Yeah. You're right. Yeah.
Exactly, and now it looks very similar to things we've done before.
Right. And now you could just you could multiply. You could get something. I actually don't want this to be multi-line. Oh, what? That looks very weird. There we go.
Yeah, without the quotient thing. But yeah, exactly. Exactly, and you can then also note that we don't really need the absolute values because n will be at least 1, so n plus 1 will also be positive. So we don't really.
Right. And we're solving
Exactly,
for n.
now you. Exactly, because we want to find some conditions on n.
Yep. So something like that. Or I guess more simply, I did that in a convoluted way.
Wait. It is a bit complicated. I think you can just divide by epsilon and then subtract 1.
Yeah, I did that in a very weird way.
Okay. Exactly. Okay. That's fine. That's fine. Exactly. So we so we have some condition on our n, right?
Yeah, yeah.
Whereas in we have to, if we make sure that our big N, our small n, is at least this, then we're good. So now we can choose our capital N to be, well, again, the seeding trick, the Archimedean principle, the same old game. Although I guess if we're being like pedantic again, we should make sure that it's actually like a natural number, because like 1 over epsilon could be like very close to 0, then the 1 over epsilon minus 1 could be like very close to -1, so its ceiling would be equal to 0, which I don't think in this case we consider as a natural number. But yeah, pedantic again.
Choose n equals 1 over epsilon minus 1. Or could we choose this as this is a little confusing here.
What do you mean?
Could we choose this as 1 over epsilon just by itself, because that's greater? Like does the minus
that could
1...
work. Yeah, that's. And then make sure to put a ceiling at the end again, because that's again even greater and it's now a natural number. But yeah, exactly. This is a perfectly good solution.
Yeah. Okay. And then we can work backwards from we are showing for all n. These are all kind of if and only ifs, actually. This could be...
Exactly. That's what we're using, right? So that we can go the other way.
Yeah. Yeah. So this is... We can just do this.
Oh, damn. Wait, what happened?
But they'll be kind of in reversed order.
Oh, that's very cool. Some magic going on here.
This is a little... and this, I mean... I should say, I guess...
And then I guess you should... Sorry, or you should say, you can kind of do the final step, right? Where you untangle this 1 over n plus 1 into n over n plus 1 minus 1.
Right.
To make it like more clear.
Yes. Yeah. I guess right here on this line at 56, I'm a little like, should I say what my small n is? Do I have to declare that somewhere?
Yeah, you should say like let small n bigger than let small n be a natural number bigger or equal to big N. but again, we have to let it be arbitrary. So, and then I guess the in between bets, then you say because small n is bigger or equal to big N, therefore we have this first inequality in the chain of inequalities that we have.
Right. I see. And that sets everything up. Okay. Yeah.
I have to say that inequality with the natural numbers being bigger than capital N, that's kind of correct.
I was hoping you would notice that.
I mean, M7, really, yeah.
Should I just split it into is that better?
Yeah, exactly. This is
that's a little.
I mean, this is
yeah,
exactly. This is how and then I mean, in the end, I don't know, if you hand it in, I would always like have a concluding sentence, therefore, and then whatever you wanted to show is true. But that's fine. So someone in chat asked, Alexander asked if we needed, or was it? Why do we enforce that capital N is a big natural number? And that's a good question. As in, it's not really necessary. It's just a definition that we made, which is fine because of the Archimedean principle. And it's just because we're talking about sequences here, right? Sequences are always indexed by natural numbers. But you can do very similar things with limits. And once you talk about the limit of a function, this will be like a delta, which will take the role of the n. And this delta can be any real number. So it's not really
right.
that use. It's just we have made this definition. Let's stick to it. But you can make also, I don't know if you, in your school, do they give like for undergrads, I mean, I hope so, but do they give like an introductory topology class?
They do, yeah. I haven't taken that yet, but I'm very curious about topology.
Topology can be very cool. I mean, I have to warn you, I should say that at the beginning, it can be very dry and just doing set theory proofs. But it's like it's something like so fundamental in mathematics nowadays. Really, you cannot escape it. So I would definitely recommend doing it.
What is topology really?
That's a good question. That's a hard question. So, I mean, and many people have a very different answer. But so we were talking about like last time, right? About like what is a metric space, kind of, right? We had the real numbers and we had their distance on them by doing like you take the difference and you take an absolute value.
Yeah.
And this kind of behaves like a distance function. We argued by like the triangle inequality, which has like the straight line distance is always the shortest, something like this.
Yeah.
And so you can abstract the real numbers into a metric space. So a metric space is any set together with the data of a metric on it, which is a function satisfying some axioms like the triangle inequality, which makes sense of a notion of distance.
Yes.
And then as soon as you have a metric space, you can kind of talk about these things like limits, whatever, continuity later of functions, because you'll see that continuity will be defined in terms of like a limit converging. So you can make sense of it. But then it turns out that you can make sense of continuity in a metric space if you have something called a notion of something called an open set, satisfying, again, some axioms, and what it is isn't really relevant. Or in the real numbers, for example, you can think of like open intervals. And it turns out that as soon that you can, your notion of continuity in this metric space only depends on this notion of what sets are open and not. So what people have done in topology is saying like, well, what if we had a set and we forgot like the metric function? What if we only had the notion of these open sets?
Okay.
and again satisfying some very, very basic axioms, and then that thing, like this set, together with some sets, the data of calling some sets open, this is what you call a topological space. And this is something incredibly general. It's truly, really, really general. I mean, I could write down the definition, but it's so general that it's not really saying that much. You know what I mean?
Yeah.
So, and it's kind of, so this topological space somehow it's a very general notion of like having a space and doing geometry in it.
Yeah.
So that's like how do you actually do it? But then what topologists actually do, or well, what people actually care about, or like popular science topology is like, in topology you kind of do geometry, but you don't care about the notion of, let's say, distance or angle or things like that. Kind of, we said it's like beyond distance. You only care, I always think about it doing qualitative geometry instead of quantitative geometry, like the usual, right? You care about things like, I have a shape, how many holes does it have? Like I'm allowed to deform my shape. This will change distance, angles, whatever you like, but it won't change the number of holes or other properties, more abstract. Things like that. So that's kind of it. And it's a bit hard to describe. I hope I'm making some sense, but it's like a really fundamental concept which shows up everywhere in modern mathematics.
Right. Yeah. Gotcha. It's one of those very type generic kind of things.
Yeah, and there's so many fields nowadays where topology is somewhere in there. Like, for example, I do algebraic geometry.
Yeah.
And it's a lot of algebra, but the kind of object I study, at the end of the day, there are also certain kinds of topological spaces, just very specific kinds.
Yeah.
And someone said in chat, Alexis again, the morphisms in the category of topological spaces are continuous functions. So topology is about continuity. That's true. So it's about, what kind of properties. Yeah, I mean, in a very technical sense, that is also, in a very abstract sense, that is like all you need to know what a topology is. Like, it preserves properties, or you care about properties that are preserved under continuous functions.
Gotcha. Yeah. All right. I guess I'm probably gonna go take a break, and I might stream later today again. Honestly, I don't know, but
yeah, I don't know. Maybe this will be in the middle of the night for me.
Cool. All right. Thanks for your help again. Appreciate it.
Yeah. Anytime.
Yeah.
Anytime.
Cool.
Okay. Yeah, I mean, maybe I'll see you around, but